Kurt Gödel sits at a strange junction in human thought. A mathematician who shattered mathematics, a logician who proved logic incomplete, a rationalist who believed in God and the afterlife, a realist about abstract objects who argued time itself might be ideal. Born in 1906 in what is now the Czech Republic, dying in 1978 in Princeton, New Jersey, Gödel produced work that reverberates through mathematics, physics, philosophy, computer science, and cognitive science, with a force that has not diminished. Here's what makes Gödel different from most thinkers. He did not write manifestos or build grand philosophical systems in prose. Instead, he constructed mathematical proofs that carried philosophical weight, theorems that forced anyone who understood them to rethink the nature of truth, knowledge, proof, time, and existence itself. His famous Incompleteness Theorems from 1931 demonstrated something shocking about formal systems. His rotating universe solution from 1949 showed that Einstein's equations allowed for time travel. His ontological proof, kept private until near death, attempted to demonstrate God's existence through pure logic. But beyond these landmark results, Gödel held a coherent philosophical worldview, what he called rationalistic, idealistic, optimistic, and theological. He believed in the power of human reason to grasp objective truths about an abstract realm. He thought mathematics described a real world of concepts that existed independently of human minds. He was convinced that every meaningful problem has a solution, even if current methods cannot find it. And he believed this commitment to reason and abstract reality pointed toward something beyond the physical. Understanding Gödel requires grasping how his mathematical work and philosophical views intertwined. The incompleteness theorems were not just technical results. They emerged from and supported his Platonism about mathematics. His work on relativity connected to his views about the nature of time. His ontological proof expressed his rationalist conviction that pure thought could reach metaphysical truths. Every piece fits into a larger vision. This exploration will unfold in parts, each examining a major dimension of Gödel's thought. We begin with what made him famous, the incompleteness theorems. Then we move through his philosophy of mathematics, his contributions to set theory and logic, his work in physics and cosmology, his engagement with idealism and the nature of time, his ontological argument, and finally, his broader philosophical commitments and influence on leading thinkers. Part 1. The Incompleteness Theorems. In the summer of 1930, Kurt Gödel was 24 years old, recently graduated with his doctorate, and thinking about the foundations of mathematics. The prevailing mood among the mathematical elite was optimistic, almost triumphant. David Hilbert, perhaps the most influential mathematician of the era, had proposed an ambitious program. He wanted to put all of mathematics on a secure foundation by finding a complete and consistent set of axioms from which every mathematical truth could be derived through mechanical rules. The idea was to eliminate doubt, ambiguity, and paradox from mathematics forever. Many believed this goal was within reach. Gödel later described how he approached the problem. He started thinking about the consistency of analysis, a branch of mathematics dealing with continuous functions and calculus. As he worked on this, he realized he needed to use the concept of truth for arithmetic, the basic mathematics of counting and calculation, to verify the axioms of analysis. This was already strange. The relationship between truth and provability, between what is true and what can be proven, became the focus of his thinking. Within months, Gödel had discovered something that would stun the mathematical world. He announced his results at a conference in Königsberg in September 1930, though many in attendance did not immediately grasp their significance. John von Neumann, one of the few who understood, reportedly stayed up all night after hearing Gödel present, and within days had worked out the second incompleteness theorem as a corollary. What Gödel proved came in two parts, now called the first and second incompleteness theorems. Let me explain them without technical symbols, focusing on what they mean. The first incompleteness theorem says this: any consistent formal system that is powerful enough to express basic arithmetic will necessarily be incomplete. Incomplete means there will be statements in the language of that system that are true, but cannot be proven within the system. No matter how many axioms you start with, no matter how clever your rules of inference, if your system can do basic arithmetic and is consistent, then it cannot prove all truths about numbers. The second incompleteness theorem goes further. Such a system cannot prove its own consistency. If your mathematical system is consistent, it cannot prove that fact about itself using only its own rules and axioms. This means mathematics cannot establish its own reliability from within. Now, these statements are profound but abstract. Let me unpack the reasoning behind them and explain why they matter so deeply. Gödel's proof works through an ingenious, self-referential construction. He showed how to encode statements about a formal system within that system using the system's own notation. This encoding, now called Gödel numbering, assigns a unique number to every symbol, formula, and proof in the system. Through this numbering, statements about provability can be translated into statements about arithmetic. This is the technical wizardry that makes everything work. Gödel found a way to make mathematics talk about itself. Using this encoding, Gödel constructed a specific sentence, call it G, that asserts its own unprovability. In ordinary language, G says, this sentence cannot be proven in this formal system. Now, think about what happens. If the system can prove G, then G is false. But that would mean the system proves false statements, making it inconsistent. If the system is consistent, it cannot prove G. But if it cannot prove G, then G is true. There really is a true statement the system cannot prove. The system is incomplete. This is reminiscent of the liar's paradox, where someone says, I am lying. But Gödel's construction avoids the paradox by moving to a mathematical context where we can establish truth independently of provability. The Gödel sentence is not paradoxical. It is simply a true statement that happens to be unprovable within its own system. The underlying assumptions matter here. Gödel's proof applies to formal systems that are consistent and sufficiently powerful. Consistent means the system never proves both a statement and its negation. It never contradicts itself. Sufficiently powerful means the system can express basic facts about numbers and perform elementary arithmetic operations. Nearly every foundational system for mathematics meets these criteria. Piano arithmetic, set theory, any system mathematicians actually use for serious work, all fall under Gödel's theorems. One immediate consequence shook the mathematical establishment. Hilbert's program was impossible. There could be no complete and consistent axiomatization of mathematics. No finite set of axioms and rules could capture all mathematical truth. The dream of reducing mathematics to a mechanical procedure, where every question could be decided by following algorithmic steps, was over. Mathematics would always require creativity, insight, and genuinely new ideas beyond what any fixed system could generate. But the implications spread far beyond the technical foundations of mathematics. Gödel's theorems revealed something about the relationship between truth and proof, between knowledge and formal systems, between what exists and what we can establish. Consider what it means for truth to transcend provability. We can recognize the Gödel sentence as true, even though the formal system cannot prove it. This recognition happens through a kind of informal reasoning that steps outside the system. We use our understanding of what the system can and cannot do to see that G must be true. This suggests human mathematical insight involves something that cannot be fully captured by any fixed set of rules. The second incompleteness theorem has its own profound implications. A mathematical system cannot certify its own consistency. To prove your axioms are coherent, you need to step outside them and use stronger assumptions. This creates a kind of hierarchy. You can prove the consistency of one system by working in a stronger system, but then that stronger system faces the same limitation. There is no ultimate foundation, no bedrock where mathematics can prove its own coherence without appealing to something beyond itself. Some philosophers and mathematicians saw this as disastrous. Others found it liberating. The idea that mathematics has an inexhaustible depth, that there will always be new truths to discover that cannot be reached by current methods, meant the mathematical enterprise would never become mechanical or complete. Human creativity would always be necessary. Now let us examine the relationship between Gödel's theorems and his philosophical commitments, particularly his mathematical Platonism. This connection is crucial, but often misunderstood. Platonism in mathematics is the view that mathematical objects and truths exist independently of human minds and formal systems. Numbers, sets, functions, these are not human inventions or mere symbols we manipulate. They are real entities in an abstract realm, and mathematics is the science of discovering truths about that realm. Mathematical truth is objective, not a matter of convention or construction. Gödel was an unabashed Platonist throughout his adult life. He believed mathematics describes a reality as objective as the physical world, just more abstract. And his incompleteness theorems supported this view, at least in his interpretation. Here's the connection. If mathematics were merely about formal systems, if mathematical truth just meant provability within some axiomatic framework, then the incompleteness theorems would be puzzling, but not philosophically dramatic. They would simply show that different formal systems have different capabilities, and that is that. But if there is a reality of mathematical truth independent of any formal system, then the theorems reveal something profound, that this reality outruns what any fixed set of rules can capture. Truth is bigger than proof. The mathematical universe has a richness that cannot be exhausted by any systematic method. Gödel himself made this point explicit in his philosophical writings. He argued that his theorems showed mathematical truth cannot be reduced to formal provability. There are arithmetical truths that are true in an objective sense, even though particular formal systems cannot establish them. This gap between truth and provability makes sense only if mathematical truth has an objective existence beyond human formal systems. Some anti-Platonists pushed back. If you do not believe in an independent realm of mathematical truths, how do you interpret Gödel's results? One response is to stay neutral about truth, and simply say that for any consistent formal system, there are statements formulable in that system that the system can neither prove nor disprove. This is undecidability. Without any claim about whether the undecidable statements are really true or false, the sentence G is undecidable in system S, that is all we can say. But Gödel found this position untenable. He pointed out that we can establish the truth of the Gödel sentence through informal reasoning. We recognize it as true by understanding what the formal system can accomplish. This recognition happens in what Gödel called intuition, a faculty of grasping mathematical truths that is not reducible to following mechanical rules. If our intuition can see truths that formal systems miss, this suggests we have access to mathematical reality beyond what any fixed procedure provides. The debate continues to this day. Formalists, constructivists, and other anti-realists have developed sophisticated responses. But Gödel's interpretation remains influential. Many working mathematicians are Platonists without necessarily articulating it. They feel they are discovering pre-existing truths, not inventing arbitrary games. Gödel gave this intuition philosophical and mathematical backing. Now let us look at some specific examples and applications of the incompleteness theorems to make them more concrete. One famous undecidable statement is the continuum hypothesis. This concerns the sizes of infinite sets. Cantor showed there are different sizes of infinity. The set of natural numbers, 1, 2, 3, and so on, is infinite, but the set of real numbers, all possible decimal expansions, is a bigger infinity. The continuum hypothesis asks whether there is any size of infinity between these two. Is there a set larger than the natural numbers but smaller than the real numbers? Gödel himself made progress on this question in 1938 by constructing a mathematical universe called the constructible universe L, where the continuum hypothesis is true. Paul Cohen later proved in 1963 that there are also mathematical universes where the continuum hypothesis is false. Together, these results show the continuum hypothesis is independent of the standard axioms of set theory. It is undecidable in ZFC, the Zermelo-Fraenkel axioms with the axiom of choice. This is not quite an example of Gödel's incompleteness theorems directly, since the continuum hypothesis is about sets rather than arithmetic, but it illustrates the same phenomenon. Fundamental questions can be undecidable within standard foundational systems. Another example is the halting problem from computer science. Alan Turing, building on Gödel's work, showed that there is no algorithm that can determine for an arbitrary computer program and input whether the program will eventually stop running or continue forever. This undecidability result flows from the same self-referential reasoning Gödel used. If you could decide the halting problem algorithmically, you could resolve the Gödel sentence, which is impossible. The halting problem is the computational analog of incompleteness. There are also undecidable statements that arise naturally in different branches of mathematics. Goodstein's theorem, which makes claims about sequences of natural numbers, is true but unprovable in piano arithmetic. Kruskal's tree theorem, relevant to computer science and combinatorics, is likewise unprovable in standard systems, but provable in stronger ones. These are not artificial constructions. They are questions mathematicians actually care about that happen to exceed the proving power of particular formal systems. The philosophical upshot is this: Incompleteness is not a quirk or defect in our foundational systems. It is an intrinsic feature of how mathematics works. Any consistent system powerful enough to do serious work will have blind spots, truths it cannot reach. This affects how we understand mathematical knowledge, the limits of computation, and the nature of formal reasoning itself. Let me turn now to some major critiques and debates surrounding the incompleteness theorems. Not everyone accepts Gödel's interpretation or agrees about the significance of his results. One line of criticism comes from strict formalists who reject Platonism entirely. They argue that mathematics is just the study of formal systems and their consequences. Truth is definable only within a system. It makes no sense to say a statement is really true but unprovable. For these thinkers, Gödel simply showed that no single formal system exhausts mathematics. We can always move to stronger systems. Mathematics is an open-ended activity of constructing and exploring different formal structures. Incompleteness is not about truth escaping proof, but about the diversity and richness of possible mathematical frameworks. This formalist response has some merit, but Gödel thought it missed the point. If we are just playing formal games, why do mathematicians care so deeply about consistency? Why does it matter that ZFC is consistent rather than inconsistent? The answer seems to be that consistency tracks something real. Whether the axioms describe a coherent mathematical universe. This points back toward realism. Another debate concerns whether Gödel's results apply to the human mind. Some philosophers, notably J.R. Lucas and later Roger Penrose, argued that incompleteness shows human minds cannot be computational systems. The reasoning goes like this. Any computer is equivalent to a Turing machine, which is equivalent to a formal system. If human minds were formal systems, they would be subject to Gödel's theorems. But humans can recognize the truth of Gödel sentences that exceed any particular formal system. Therefore, human minds are not formal systems. Therefore, strong artificial intelligence is impossible, and human cognition involves something non-algorithmic, perhaps quantum mechanical processes in the brain. This argument has generated enormous controversy. The main objection is that it confuses two things: what a formal system can prove from within, and what we can establish about the system from outside. When we recognize a Gödel sentence as true, we are reasoning informally about what a formal system can do. We are not operating within the system. A sufficiently sophisticated computer could also reason about other computers and recognize when they cannot prove certain statements. The fact that we can see truths about formal systems does not prove we are not formal systems ourselves. It just shows we can reason at multiple levels. Penrose responded that human mathematical intuition involves a direct grasping of truths that cannot be algorithmic. We perceive mathematical reality through a faculty that is not reducible to rule following. This perception might involve quantum processes in neural microtubules that collapse wave functions in ways relevant to consciousness. But most philosophers and neuroscientists find this speculative and unnecessary. There is no evidence that quantum effects play a role in ordinary cognition, and the jump from Gödel's theorems to quantum consciousness seems to involve several non sequiturs. What did Gödel himself think about minds and machines? This is fascinating. He was skeptical that human reason could be fully mechanized, but not for the reasons Lucas and Penrose suggested. Gödel thought human mathematical intuition gave access to objective truths that went beyond any formal system. This intuition was not algorithmic, but it was also not mysterious or quantum mechanical. It was a rational faculty for grasping concepts and their relationships. The power of this faculty, in Gödel's view, made it unlikely that we are equivalent to Turing machines. But he never claimed to have a proof of this. It was more a philosophical conviction based on his Platonism and rationalism. There are other philosophical ramifications worth exploring. Incompleteness has been invoked, sometimes correctly and sometimes not, in discussions about the limits of science, the nature of truth in ethics and metaphysics, the foundations of legal reasoning, and even theology. Let me separate legitimate applications from overreach. In science, incompleteness suggests that no finite set of physical laws can entail every true statement about the universe, if we assume the universe includes structures capable of encoding arithmetic. This is speculative. Physical reality might not work like a formal system. But if the laws of physics can be modeled mathematically in a sufficiently rich way, there could be questions about the physical world that cannot be settled by the laws themselves. Some physicists have noted that certain problems in quantum gravity or cosmology might be formally undecidable. In ethics and metaphysics, the application is more dubious. Some have argued that incompleteness shows moral truth cannot be systematized, or that metaphysical questions have no definitive answers. But Gödel's theorems apply to formal systems that include arithmetic. Moral reasoning might not be formalizable in the relevant sense, and even if it were, undecidability within a system does not mean there is no truth, just that the truth might require resources beyond the system to establish. Gödel himself believed strongly in objective truth and thought most important questions had answers, even when current methods could not find them. In theology, Gödel's work has been invoked both to support and undermine religious belief. Some argue that incompleteness shows rational thought cannot be self-sufficient, pointing toward the need for revelation or faith. Others say it demonstrates the limits of formal theology. Gödel himself was a theist with complex religious views, but he did not think his incompleteness theorems directly implied anything about God's existence. For that, he developed a separate argument we will explore later. One particularly misguided interpretation claims that incompleteness means anything goes, or that there are no objective truths. This gets it backwards. Gödel showed that truth exceeds what any fixed formal system can prove. This distinction makes sense only if we assume there is objective truth to begin with. Incompleteness is not about the absence of truth, but about the inability of systematic methods to capture all of it. Let me address one more subtle issue: the philosophical question of whether there exist absolutely undecidable statements. An absolutely undecidable statement would be one whose truth or falsity cannot be determined by any means, formal or informal. Gödel's theorems establish relative undecidability, statements undecidable in particular systems. But could there be statements with no determinate truth value whatsoever? Gödel rejected this possibility. As a Platonist, he believed every well-formed mathematical statement has a definite truth value, even if we never discover it. The Gödel sentence is true, not somehow indeterminate. The continuum hypothesis is either true or false in the mathematical universe, even though it is independent of ZFC. We might not know which, but there is a fact of the matter. Others disagree. Intuitionists and constructivists argue that mathematical truth depends on constructive proof. A statement is true only if we have a method of establishing it, false only if we can refute it, and otherwise neither true nor false. From this perspective, absolutely undecidable statements would be meaningless, lacking any truth value. The debate touches on fundamental questions in the philosophy of mathematics about what truth means and whether it can exist independently of proof or knowledge. The impact of Gödel's incompleteness theorems on mathematical practice has been less dramatic than their philosophical implications. Most working mathematicians go about their business without worrying much about undecidable statements. In practice, the undecidable statements that arise naturally tend to be exotic or concern foundational issues. Ordinary mathematical questions usually can be settled within standard systems. But the theorems changed how mathematicians think about the foundations of their discipline. There's a background awareness that mathematics rests on assumptions that cannot be fully justified from within, and that the mathematical universe is inexhaustible. The incompleteness theorems also influence the development of mathematical logic, set theory, and computer science in concrete ways. They led to the theory of recursive functions and computability. They motivated investigations into different axiom systems and their relative strength. They prompted questions about what can and cannot be computed, algorithmic information theory, and the foundations of artificial intelligence. Gödel's work opened entire fields of inquiry. Finally, there's the question of whether we have fully understood the philosophical significance of incompleteness. 3 generations after Gödel's proof, philosophers and mathematicians continue to debate what it means. Does it show that human reason has limits, or that it has inexhaustible power? Does it support Platonism, or undermine it? Does it reveal something about consciousness, or is it purely a technical result in mathematical logic? These questions remain open, testimony to the depth and lasting impact of what Gödel discovered in 1930. Part 2. Mathematical Platonism and the Reality of Concepts. Kurt Gödel believed that numbers exist, not as physical objects you can touch, not as neurons firing in human brains, not as symbols on paper, but as real entities in an abstract realm with objective properties independent of anyone's thoughts about them. This position, called mathematical Platonism or realism, was the bedrock of his entire philosophical outlook. Everything else he thought about mathematics, logic, knowledge, and truth flowed from this conviction. But what does it mean to say that numbers or sets exist when they clearly are not physical? How could we possibly know anything about objects that do not exist in space or time? And if mathematics is about discovering truths in an independent realm, what faculty allows us to perceive these truths? These questions obsessed Gödel throughout his life, and his answers reveal a sophisticated philosophical position that goes far beyond naive Platonism. Let me start with what Gödel actually meant by Platonism. He defined it carefully in his published work and conversations. In his 1951 Gibbs lecture, he characterized realism or Platonism as the view that mathematical objects and facts exist objectively and independently of our mental acts and decisions. Mathematical truth is not created by mathematicians, it is discovered. When we prove the Pythagorean theorem, we are not inventing a relationship between the sides of right triangles. We are uncovering a truth that held before humans existed and would continue to hold even if all minds vanished from the universe. This might sound obvious to working mathematicians, many of whom operate as if they are exploring a pre-existing landscape, but it is philosophically controversial. The main alternative views are formalism, which treats mathematics as the study of formal symbol systems without reference to any external reality, and constructivism or intuitionism, which holds that mathematical objects are mental constructions, and mathematical truth depends on proof or construction by mathematicians. Gödel rejected both alternatives. Against formalism, he pointed out that mathematicians care about consistency and truth, not just syntactic manipulation. We do not choose axioms arbitrarily. We select them because we believe they accurately describe mathematical reality. Against constructivism, he argued that limiting mathematical truth to what we can construct or prove is arbitrary and restrictive. There are infinitely many mathematical truths we will never prove. Does that make them not true? Gödel thought this was absurd. His Platonism extended beyond objects to concepts. This is crucial and often overlooked. Gödel was not just claiming that individual numbers or sets exist. He believed that mathematical concepts have objective reality. The concept of set, the concept of number, the concept of function, these are not arbitrary human inventions, but objective features of reality that we grasp through intuition. This focus on concepts rather than just objects gave Gödel's Platonism a distinctive character. It connected to his engagement with phenomenology, which we will explore later. For now, note that concepts are in some sense more fundamental than particular objects. Understanding the concept of set allows us to reason about all sets, not just particular examples. Mathematical knowledge proceeds by clarifying and analyzing concepts. Now let us examine Gödel's argument for Platonism. He did not simply assert it, he tried to provide rational justification. His main argument appears in the Gibbs lecture and in his papers on set theory from the 1940s. The argument runs roughly like this. Consider how mathematics actually works. Mathematicians propose axioms, derive theorems, and develop theories, but they do not choose axioms capriciously. They select axioms that seem evident, that capture our intuitive understanding of the mathematical domain in question. For example, the axioms of set theory codify our intuitive concept of collection. When mathematicians discover that certain axioms lead to paradoxes or contradictions, they revise them. This process makes sense only if there is an objective reality the axioms are trying to capture. We revise our axioms when they fail to describe mathematical reality accurately. Furthermore, consider how mathematical concepts get clarified over time. The concept of number, for instance, was initially vague. Through mathematical work spanning centuries, it became precise. We now understand natural numbers, integers, rational numbers, real numbers, complex numbers, each a clarification and extension of the initial concept. This process resembles scientific investigation more than arbitrary invention. Mathematicians are exploring a territory, gradually mapping it with increasing precision. Gödel also appealed to the applicability of mathematics. Mathematical structures discovered purely for their intrinsic interest often turn out to describe physical reality with uncanny accuracy. Non-Euclidean geometry, developed as a purely mathematical exercise, became essential for general relativity. Complex numbers, initially considered bizarre fictions, are indispensable in quantum mechanics. This suggests mathematics is not just a game we play, but a description of objective structures that happen to be realized in nature. The Incompleteness Theorems provided another argument. We have already seen how Gödel interpreted them as showing that truth exceeds provability. Mathematical truth cannot be reduced to what any formal system can establish. This makes sense if truth is objective, existing independently of our methods of discovering it. If mathematical truth were just whatever we can prove, incompleteness would mean mathematics is infected with indeterminacy. But if truth is objective, incompleteness just shows our methods are limited, not that truth itself is incomplete. Despite these arguments, Gödel admitted he could not prove Platonism in any decisive way. In his conversations with the philosopher Hao Wang, he expressed frustration about this. The best he could do, he thought, was to enumerate all the alternative positions: formalism, constructivism, nominalism, and show why each was inadequate. If you eliminate every alternative, what remains must be correct. But this dialectical approach never fully satisfied him, because he could not be certain he had considered every possible alternative. This brings us to mathematical intuition, perhaps the most controversial aspect of Gödel's philosophy. If abstract mathematical objects exist, how do we know about them? We cannot see numbers or touch sets. We cannot perform experiments on mathematical concepts. Yet mathematicians have knowledge of this abstract realm. Gödel's answer was intuition, a faculty of directly perceiving or grasping mathematical truth. But intuition sounds dangerously mystical. It evokes images of special powers, ineffable insights, or even supernatural revelation. Gödel was aware of this problem and tried to make his notion of intuition respectable and naturalistically acceptable. He did not succeed in convincing everyone, but his position is more sophisticated than critics often acknowledge. For Gödel, mathematical intuition was not a mysterious sixth sense. It was the faculty by which we grasp concepts and recognize their properties. When a mathematician understands what a set is, when they comprehend the concept of continuity or infinity, this understanding is intuitive in Gödel's sense. It is not learned by rote memorization of definitions. It involves a direct intellectual perception of the concept's meaning and implications. Gödel compared mathematical intuition to sense perception, not because they are identical, but because both involve direct contact with reality. Just as vision gives us immediate awareness of physical objects, mathematical intuition gives us immediate awareness of abstract objects and concepts. Both are fallible. We can misperceive physical objects just as we can misunderstand mathematical concepts. But both put us in cognitive contact with objective reality. This analogy with perception runs deep in Gödel's thinking. He believed that just as sense perception evolved to track features of the physical environment relevant to survival, mathematical intuition evolved or developed to track features of abstract reality relevant to rational thought. The process by which we clarify mathematical concepts resembles the process by which we learn to perceive the physical world more accurately. Critics jumped on this immediately. Perception involves causal interaction between physical objects and sense organs. Light from an object strikes the retina, initiating a causal chain that produces visual experience. But abstract objects are causally inert. They exist outside space and time and cannot interact with anything physical. So how could we possibly perceive them? This is the famous epistemological problem for Platonism, and it threatens to make mathematical knowledge inexplicable. Gödel had responses, though they did not fully dissolve the problem. First, he questioned whether causal interaction is really necessary for knowledge. Why assume that all knowledge must result from causal processes? This seems to beg the question against the possibility of knowing abstract objects. Second, he suggested that the relationship between mind and abstract reality might involve some form of intentionality that is not causal in the ordinary sense, but still allows cognitive access. This connects to his interest in phenomenology, which studies how consciousness is directed toward objects. Third, and perhaps most importantly, Gödel thought the problem of mathematical knowledge was no more mysterious than the problem of any knowledge. Even knowledge of physical objects is philosophically puzzling. How do patterns of neural activity give rise to awareness of an external world? How does subjective experience connect to objective reality? These questions apply to all knowledge, not just mathematical knowledge. If we cannot solve them in general, it is no special objection to Platonism that mathematical knowledge faces similar difficulties. Still, many philosophers found Gödel's appeals to intuition unsatisfying. Without a clearer account of how intuition works, how we can distinguish genuine intuition from error, and what justifies trusting intuitive judgments, the notion seems to leave mathematical knowledge resting on a mysterious foundation. This criticism had force, and Gödel struggled with it throughout his philosophical career. One important clarification: Gödel distinguished different types of intuition. There's intuition of individual objects or simple facts, and there is intuition of concepts and their relationships. The latter is more fundamental. We do not intuit particular numbers one by one. We grasp the concept of number, and from that concept we can reason about all numbers. This conceptual intuition is what allows mathematics to be systematic, rather than just a collection of isolated intuitive judgments. Gödel also believed mathematical intuition could be improved and refined through intellectual work. It is not a fixed faculty that some people have and others lack. By studying mathematics, thinking carefully about concepts, and working through proofs, mathematicians sharpen their intuitive grasp of mathematical reality. In this sense, intuition is not prior to mathematical reasoning, but develops through it. This raises questions about mathematical practice that Gödel addressed throughout his work. If mathematics is about discovering truths in an objective realm, what role do axioms play? How do we justify adopting new axioms? And what happens when different axiom systems are incompatible? Gödel's view was that axioms should be evident. They should be statements that we recognize as true when we clearly grasp the relevant concepts. The axioms of set theory, for example, should capture what we intuitively understand sets to be. When we say that for any property, there's a set of all things with that property, this seems evident from the concept of set as collection. When we later discover this leads to paradox, we revise our understanding. Perhaps unrestricted comprehension was not part of the true concept of set after all. This means axioms are not arbitrary starting points chosen for convenience. They are attempts to codify our intuitive grasp of mathematical structures. Good axioms are those that accurately describe the domain they are meant to formalize. Bad axioms are those that misrepresent or incompletely capture the intended structures. But here's where things get complicated. Gödel believed there were mathematical facts not settled by current axioms. The continuum hypothesis, for instance, is independent of standard set theory. Yet Gödel thought it has a determinate truth value. Either there is a size of infinity between the natural numbers and the real numbers, or there is not. This is an objective fact about the mathematical universe, even though our current axioms do not decide it. How can we discover such facts? Gödel's answer was that we need new axioms, not arbitrary additions to the system, but axioms that capture further aspects of mathematical reality that our current axioms miss. He believed such axioms would eventually be found through conceptual analysis, by clarifying our understanding of the concept of set and recognizing what that concept implies. This connects to his work on large cardinal axioms, which we will explore in the next part. For now, note the philosophical picture. mathematics proceeds by an iterative process of intuition, axiomatization, and conceptual refinement. We grasp mathematical concepts intuitively. We formalize this understanding in axioms. We discover the implications of those axioms. Sometimes we find our axioms were inadequate or led to contradictions, so we revise them. Sometimes we find our axioms do not settle all questions, so we add new ones. Throughout this process, we are trying to align our formal systems with the objective mathematical reality we intuit. Let me turn now to how Gödel's Platonism differs from other forms of mathematical realism. The history of philosophy contains many varieties of Platonism, and Gödel's version has distinctive features. Classical Platonism, deriving from Plato himself, posits a realm of perfect forms or ideas that physical reality imperfectly instantiates. Mathematical objects are among these forms. The number 3 exists eternally and perfectly in the realm of forms, while groups of 3 physical objects are imperfect manifestations of this ideal. Knowledge of mathematical objects comes through rational insight that transcends sensory experience. Gödel's Platonism shares the basic commitment to abstract objects existing independently of minds, but it is less mystical and more focused on classical Platonism. He was not particularly interested in the relationship between abstract forms and physical instantiations. His concern was with how we gain knowledge of mathematical structures through conceptual analysis and rational intuition. Frege and Russell, early 20th century figures who influenced Gödel, developed versions of logicism that combined Platonism with the idea that mathematics reduces to logic. They believed mathematical truths are ultimately logical truths, and mathematical objects are logical objects. Gödel rejected this reduction. Mathematics cannot be reduced to logic because mathematical concepts like set or number are not definable purely in logical terms. Mathematics has its own subject matter, distinct from logic, even though the two are closely related. More recent versions of mathematical realism, developed after Gödel, include structural realism, which holds that mathematical objects are positions in structures rather than independent entities. What matters is not the intrinsic nature of the number 3, but its position in the structure of natural numbers. Gödel would likely have found this congenial, but incomplete. Structures are themselves abstract entities that need to exist objectively if realism is to be maintained. Another form of realism is mathematical naturalism, which tries to make Platonism compatible with naturalism by explaining mathematical knowledge in terms of natural cognitive processes. Perhaps our brains are wired through evolution to track abstract structures that happen to be useful for navigating the physical world. Gödel would have been skeptical. He did not think mathematical knowledge could be explained naturalistically without remainder. The fact that we can grasp infinitary concepts like the set of all natural numbers, which vastly exceeds anything we encounter in physical experience, suggests our mathematical capacities transcend what naturalistic evolution would produce. Now I must address the most common criticism of mathematical Platonism, the epistemological problem I mentioned earlier. If mathematical objects exist outside space and time and cannot interact causally with anything, how is mathematical knowledge possible? This objection has been pressed by nominalists and empiricists repeatedly, and it remains the main reason many philosophers reject Platonism. Paul Benacerraf formulated an influential version of this objection in a 1973 paper. He argued that any adequate account of mathematical knowledge must show how mathematical beliefs are reliably correlated with mathematical facts. For ordinary knowledge, causal interaction explains this correlation. I believe there is a tree in front of me because the tree causes certain sensory experiences. But abstract objects cannot cause anything. So what explains the correlation between mathematical beliefs and mathematical facts? If there is no explanation, Platonism makes mathematical knowledge a lucky accident or a mystery. Platonists have offered various responses. Some deny that causal interaction is necessary for knowledge. Perhaps there are non-causal forms of epistemic access, such as rational insight or conceptual grasping. Others argue that the correlation between beliefs and facts can be explained by the fact that both are constrained by logic and conceptual necessity. We cannot coherently believe 2 + 2 = 5, because that violates the concept of addition. The necessity built into mathematical concepts ensures our beliefs align with mathematical reality when we reason correctly. Gödel's response, as we have seen, emphasized conceptual intuition and the analogy with perception. He did not think the epistemological problem for mathematical knowledge was fundamentally different from the epistemological problem for any knowledge. All knowledge faces the question of how subjective mental states can accurately represent objective reality. This is a deep problem in philosophy of mind and epistemology, but it is not a special problem for Platonism. Some contemporary philosophers have developed what they call indispensability arguments for mathematical realism. The idea is that mathematics is indispensable to our best scientific theories. We cannot do physics without using mathematical structures. If we are realists about science, if we think scientific theories describe objective reality, then we should be realists about the mathematical structures they employ. This argument was not available to Gödel in the same form, but he would likely have endorsed it as supporting his position. There is one more aspect of Gödel's philosophy of mathematics worth exploring: his views on the relationship between mathematical truth and linguistic or symbolic representation. Some philosophers argue that mathematical truth is relative to formal systems or languages. What counts as true in one system might not be true in another. This seems to follow from the existence of non-standard models in logic and the independence results in set theory. Gödel completely rejected this relativism. He distinguished carefully between mathematical truth and provability in formal systems. Truth is absolute and objective. Provability is relative to systems. The fact that different formal systems have different proving power does not mean truth itself is relative. It just means different systems give us access to different portions of mathematical reality. Similarly, the existence of non-standard models does not threaten objectivity. When we formalize arithmetic, the formal system has many models, including non-standard models with strange, infinite numbers. But this does not mean there is no fact about which model is the real natural numbers. We intend our axioms to describe the standard natural numbers, and that intention fixes what we are talking about, even if the formal system admits other interpretations. This points to a deep conviction in Gödel's thought. Meaning cannot be fully captured by formal systems. The meaning of mathematical concepts transcends any particular axiomatization. We grasp the concept of natural number through intuition, and that intuition fixes a unique structure as the intended interpretation, even though formal systems underdetermine the interpretation. This is why informal mathematical reasoning is indispensable. We can never eliminate appeals to intuitive understanding in favor of purely mechanical manipulation of symbols. Let me conclude this part by considering what hangs on the debate between Platonism and its alternatives. Why should anyone care whether mathematical objects exist independently or are human constructions? what practical difference does it make? For Gödel, the stakes were high. If Platonism is false, then mathematics has no objective truth. It becomes a game we play with symbols, constrained only by consistency. But if there is no objective mathematical truth, then incompleteness loses its philosophical significance. It merely shows that different formal systems have different capabilities. There is no gap between truth and provability, because there is no truth independent of provability. Furthermore, without Platonism, Gödel thought we could not make sense of mathematical progress. Why do mathematicians work to improve axiom systems, to resolve open problems, to clarify concepts? If there is no objective reality they are investigating, this activity seems pointless. With Platonism, mathematical progress consists in gradually uncovering the structure of an objective domain. We get better at describing mathematical reality. Without Platonism, progress is just movement from one arbitrary formal system to another. Finally, Platonism matters for Gödel's broader philosophical outlook. His rationalism, his optimism about human knowledge, his theological commitments, all depend on the existence of an objective realm of abstract truths that reason can grasp. If Platonism fails, much of Gödel's worldview collapses with it. This is why he devoted so much effort to defending and articulating his mathematical realism. Yet for all his arguments, Gödel never claimed to have proven Platonism beyond doubt. He recognized it as a philosophical position with competitors, even as he believed it was the only tenable position. His work in logic and mathematics aimed to support Platonism indirectly by showing what follows from it and why alternatives face difficulties. Whether he succeeded remains debated to this day, but his sophisticated defense of mathematical realism stands as one of the most important contributions to philosophy of mathematics in the 20th century. Part 3. Set Theory and the Continuum Problem. In 1938, 7 years after his Incompleteness Theorems revolutionized logic, Kurt Gödel made another breakthrough that would reshape mathematics. He constructed a mathematical universe, a model of set theory, where the continuum hypothesis is true. This work, on what is now called the constructible universe L, represented not just a technical achievement, but a philosophical statement about the nature of mathematical reality and how we can investigate it. To understand what Gödel accomplished and why it matters, we need to grasp what set theory is, what the continuum hypothesis asks, and why mathematicians cared so deeply about resolving it. This requires diving into some of the most profound and strange aspects of mathematics, the mathematics of infinity. Set theory began in the late 19th century with Georg Cantor's revolutionary work. Cantor showed that not all infinities are equal. There are different sizes of infinity. The set of natural numbers, 1, 2, 3, 4, and so on forever, is infinite. But the set of real numbers, all possible decimal expansions, including irrational numbers like pi and the square root of 2, is a larger infinity. There are more real numbers than natural numbers, even though both sets are infinite. This seems paradoxical. How can one infinity be larger than another? Cantor's argument is brilliant. To compare sizes of sets, we try to match them up one to one. If you compare every element of set A with a unique element of set B, with nothing left over, then A and B have the same size. Cantor showed that no matter how you try to list all real numbers, you inevitably miss some. Any supposed complete list can be used to construct a real number not on the list. This diagonal argument proves the real numbers cannot be put in one-to-one correspondence with the natural numbers. Therefore, the set of real numbers has a larger cardinality, a bigger size of infinity. Cantor went further. He showed there is an entire hierarchy of infinite sizes, called cardinalities or cardinal numbers. The cardinality of the natural numbers is denoted aleph 0. The cardinality of the real numbers is larger, but how much larger? This is where the continuum hypothesis enters. The continuum hypothesis, proposed by Cantor, states that there is no cardinality between aleph 0 and the cardinality of the real numbers. The real numbers represent the next size of infinity after the natural numbers, with no intermediate sizes. In technical notation, the continuum hypothesis says that the cardinality of the continuum equals aleph 1, the next cardinal after aleph 0. This seems like a simple question with a definite answer. Either there is an intermediate size or there is not. Cantor worked for years trying to prove the continuum hypothesis. He failed. Mathematicians after him tried. They failed too. David Hilbert, in his famous list of 23 unsolved problems from 1900, placed the continuum hypothesis first, considering it the most important open question in mathematics. Enter Gödel. In 1938, he showed that if the standard axioms of set theory, the Zermelo-Fraenkel axioms, or ZF, are consistent, then the continuum hypothesis cannot be disproved from them. He did this by constructing a specific model of set theory, the constructible universe L, where ZF holds, and the continuum hypothesis is true. If the continuum hypothesis were disprovable from ZF, then it would be false in all models of ZF, including L. Since it is true in L, it cannot be disprovable. This was only half the story. In 1963, Paul Cohen used a technique called forcing to show that the continuum hypothesis also cannot be proved from ZF. He constructed models where ZF holds, but the continuum hypothesis is false. Together, Gödel's and Cohen's results established that the continuum hypothesis is independent of ZF. The standard axioms of set theory simply do not decide whether the hypothesis is true or false. This might sound like a negative result. We cannot solve the problem. But it revealed something profound about the nature of mathematics and the limits of formal systems. The continuum hypothesis is not some strange artificial statement cooked up to be undecidable. It is a natural, fundamental question about the structure of infinity. Yet our best foundational axioms leave it open. This was the first clear example of an important mathematical question that standard axioms cannot settle. Let me explain in more detail what Gödel did when he constructed the universe L. This involves some of the most beautiful and deep mathematics of the 20th century. In set theory, we start with the empty set, the set containing nothing. From this, we build up more and more sets using operations like taking subsets, unions, and power sets. A model of set theory is a collection of sets satisfying the ZF axioms. But there are many such models, not just one. They all satisfy the same axioms, but may differ in what sets they contain. Gödel's idea was to construct the most restricted, minimal model possible while still satisfying ZF. He built sets in stages, starting from the empty set, and at each stage adding only those sets that can be defined using formulas from sets constructed at earlier stages. This process of construction involves only definable sets, which is why the resulting universe is called constructible. The constructible universe L has remarkable properties. First, it satisfies all the ZF axioms, so it is a legitimate model of set theory. Second, it satisfies the axiom of choice, one of the most controversial axioms in mathematics, which allows selecting elements from infinitely many sets simultaneously. Third, and most importantly for our purposes, it satisfies the continuum hypothesis. Within L, there is no cardinality between Aleph 0 and the cardinality of the real numbers. Why does L satisfy the continuum hypothesis? The intuition is this. By restricting to definable sets, we keep the universe as small as possible consistent with the axioms. In this minimal universe, there simply is not room for intermediate cardinalities to exist. The real numbers in L have cardinality Aleph 1 because we have not added any exotic sets that would create larger cardinalities below the continuum. This construction was technically brilliant, but what interested Gödel more were its philosophical implications. If the continuum hypothesis is independent of ZF, what does this tell us about the nature of mathematical truth? Does the continuum hypothesis have a definite truth value, or is it meaningless to ask whether it is true or false? Gödel's Platonism forced him to conclude that the continuum hypothesis is either true or false, even though ZF does not decide it. There is an objective fact about the mathematical universe concerning how many cardinalities exist between Aleph 0 and the continuum. Our axioms simply do not capture enough information to determine this fact. This means we need new axioms that better describe the intended structure we are trying to formalize. Gödel believes such axioms would come from clarifying our intuitive concept of set. What is a set? It is any collection that can be formed according to coherent principles. The ZF axioms capture some aspects of this concept, but not all. By reflecting more deeply on what sets are, we should be able to recognize additional principles, axioms that are evident once we grasp them, but not derivable from our current axioms. This is where large cardinals enter the picture. Large cardinal axioms assert the existence of very large infinite sets with special properties. These axioms go beyond ZF. They assert the existence of inaccessible cardinals, measurable cardinals, supercompact cardinals, and many other exotic infinities. Each is larger and has stronger properties than the ones before. Gödel was prophetic in anticipating the importance of large cardinals. In the 1940s, when few mathematicians paid attention to such axioms, Gödel argued they would prove crucial for set theory. He believed large cardinal axioms captured important features of the concept of set, principles about how far the hierarchy of sets extends and what kinds of infinite structures exist. More specifically, Gödel hoped large cardinal axioms might settle the continuum hypothesis. If we adopt axioms asserting the existence of sufficiently large cardinals, perhaps this would determine whether there are intermediate cardinalities. The continuum hypothesis would turn out to be true or false as a consequence of these stronger axioms that better articulate our concept of set. This hope has only partially been realized. Large cardinal axioms have proved immensely important in set theory. They provide a hierarchy of stronger and stronger foundational systems. Many questions independent of ZF are decided by large cardinal axioms. The theory of large cardinals has revealed deep connections between different areas of mathematics. But the continuum hypothesis remains independent even of most large cardinal axioms. Adding them does not settle it. However, Gödel's program of finding new axioms to settle independent questions continues. Some mathematicians believe we will eventually recognize axioms that decide the continuum hypothesis. Others think the question is inherently ambiguous, with different set-theoretic universes giving different answers. This debate cuts to the heart of mathematical philosophy. Is there a unique mathematical universe, or are there multiple, equally legitimate mathematical realities? Gödel firmly believed in a unique mathematical universe. The sets exist in a definite structure, and there's a fact of the matter about cardinalities. The multiplicity of models just reflects the inadequacy of our axioms to pin down this unique intended structure. Better axioms would converge on the true mathematical universe, just as better scientific theories converge on accurate descriptions of physical reality. Let me now explore Gödel's work on the axiom of choice, which connects closely to his work on the continuum hypothesis and constructibility. The axiom of choice states that, given any collection of non-empty sets, it is possible to select exactly one element from each set, even if the collection is infinite, and there is no rule for making the selections. This sounds innocent, but has counterintuitive consequences. It implies the existence of non-measurable sets so pathological they cannot be assigned a size or volume in any coherent way. It implies the Banach-Tarski paradox, which says a solid ball can be decomposed into finitely many pieces and reassembled into two balls of the same size as the original. An impossible feat physically, but mathematically valid under the axiom of choice. Because of these strange consequences, some mathematicians rejected the axiom of choice. They argued it asserts the existence of arbitrary, non-constructive selections that do not correspond to any well-defined procedure. Mathematics should deal only with objects we can explicitly construct or define, not mysterious objects brought into existence by sheer assertion. Gödel's constructible universe L provided an answer. He showed that if ZF is consistent, then ZF plus the axiom of choice is consistent. In L, the axiom of choice holds automatically. This vindicated the axiom of choice by showing it does not introduce contradictions. If you accept ZF, you can safely accept the axiom of choice. More philosophically, Gödel's result showed that the axiom of choice reflects something about the structure of sets. In the minimal, most restricted universe satisfying ZF, choice holds. This suggests choice is a natural principle rather than an arbitrary addition. It captures something about what sets are, even if the choices it asserts seem non-constructive. Yet Gödel himself had complex views about constructibility and what it showed. On one hand, proving the consistency of the axiom of choice and the continuum hypothesis was a major achievement. On the other hand, Gödel did not believe the constructible universe L was the true set-theoretic universe. He thought the real universe of sets is much larger than L. Why? Because Gödel believed in maximality principles. The set-theoretic universe should be as large as possible consistent with coherence. Limiting sets to only definable ones seems arbitrary and restrictive. Why would mathematical reality be constrained by what we can define? Gödel thought the true universe contains all sets that can coherently exist, not just definable ones. This created tension in his work. He proved important results about L, but he did not endorse L as the correct model of set theory. Instead, he viewed L as a tool for proving consistency results. It showed what is consistent with ZF, but not necessarily what is true about sets. Gödel's Leibnizian intuition drove his belief in maximality. Leibniz held that God creates the best of all possible worlds, the most complete and perfect universe consistent with logical possibility. Gödel adapted this to mathematics. The mathematical universe should be the fullest, richest structure consistent with logical coherence. Restriction to constructible sets would arbitrarily limit this plenitude. This connects to another aspect of Gödel's work in set theory, his interest in maximality principles as a way to extend ZF. A maximality principle says, roughly, that any set whose existence does not lead to contradiction exists. If you can coherently describe a collection, it forms a set. This principle pushes the set-theoretic universe toward maximal size and richness. Gödel speculated that proper maximality axioms would settle the continuum hypothesis. He conjectured, in fact, that the continuum hypothesis is false. His reasoning was that maximality principles should produce a rich universe with many cardinalities between Aleph 0 and the continuum. The hypothesis, which says there are no intermediate cardinalities, seems too restrictive for a maximal universe. This conjecture was tentative, and Gödel never published a detailed argument for it, but it reveals his philosophical approach, looking for axioms that extend ZF in ways that match our intuitive concept of set while settling independent questions. The continuum hypothesis would be decided not by arbitrary fiat, but by adopting axioms that better articulate what sets are. Contemporary work in set theory has explored various approaches to extending ZF. Forcing axioms, which generalize Cohen's forcing technique, have proved fruitful. Axioms asserting the existence of inner models with strong properties have revealed connections to large cardinals. Axioms based on ideas from category theory or topos theory offer alternative foundations. But no consensus has emerged about which extensions are correct, and the continuum hypothesis remains independent of all these proposals. This situation would have frustrated Gödel. His hope was that mathematical investigation would converge on evident axioms settling the major open questions. Instead, set theory has proliferated into multiple research programs with different philosophical orientations and no clear resolution. Some see this as vindication of pluralism. Maybe there is no single right answer. Others see it as evidence we have not yet found the right axioms. Let me turn to another aspect of Gödel's work in logic that connects to set theory, his completeness theorem from 1929. This is often confused with the incompleteness theorems, but it is an entirely different result with different implications. The completeness theorem says that in first-order logic, every logically valid formula is provable from the standard axioms of logic. If a statement is true in all interpretations of the logical symbols, then there is a formal proof of it. Completeness here means the proof system is strong enough to capture all logical truths, not that it can prove all truths in a given domain. This result preceded the incompleteness theorems and in some ways contrasts with them. Logic is complete. All logical truths are provable. Arithmetic and set theory are incomplete. They contain truths that cannot be proven from standard axioms. The difference lies in expressive power. First-order logic is weak enough that its truths coincide with its theorems. Arithmetic and set theory are rich enough that truth exceeds provability. Gödel's completeness theorem had important consequences. It showed that model theory and proof theory are two sides of the same coin. A statement is provable if and only if it is true in all models. This duality became fundamental to modern logic. It also showed that consistency and satisfiability are equivalent. A theory is consistent if and only if it has a model. But there is a philosophical puzzle here. Completeness seems to suggest that logic fully captures logical truth. Everything valid is provable. Yet incompleteness shows that mathematics cannot be fully captured by any axiom system. How do these fit together? The answer is that logic and mathematics have different structures. Logic deals with the form of arguments, independent of content. Any statement expressible purely in logical vocabulary, using only quantifiers, connectives, identity, and variables, is decided by logical rules. But mathematics introduces content through non-logical concepts, like number, set, function. These concepts have richness that exceeds what first-order logic can formalize. Once you add mathematical axioms to logic, you get incompleteness. Gödel saw this as revealing something deep about the nature of mathematical concepts. They are not reducible to logic. The concept of number, for instance, has a content that goes beyond anything expressible in pure logic. This is why mathematics needs its own axioms beyond logical axioms, and why those mathematical axioms inevitably leave some truths unprovable. This anti-logicist message connected to Gödel's criticism of Frege and Russell. They tried to reduce mathematics to logic, showing that mathematical truths are just complex logical truths. Gödel's completeness and incompleteness theorems together undermined this program. Logic is complete, but mathematics is not. Therefore, mathematics cannot be reduced to logic. It has its own irreducible subject matter. The completeness theorem also had technical applications that Gödel explored. It implies the compactness theorem, which says that if every finite subset of a set of axioms has a model, then the whole infinite set has a model. This leads to the existence of non-standard models, structures satisfying the axioms but looking very different from the intended interpretation. For arithmetic, compactness implies there are models with infinite numbers beyond all standard natural numbers. These non-standard models satisfy all the axioms of arithmetic, but contain bizarre elements. For set theory, there are models with different cardinalities and different hierarchies of infinities. All satisfy the axioms, but they differ radically in structure. Does this mean arithmetic and set theory are ambiguous, with no determinate intended interpretation? Some philosophers have argued yes. The axioms do not uniquely fix what we are talking about, so there is no fact about which model is correct. Mathematical truth is relative to a choice of model. Gödel rejected this forcefully. He insisted that we intend to talk about the standard natural numbers, or the full universe of sets. Our axioms may fail to capture this intention fully, but the intention is there nonetheless. Non-standard models are artifacts of the weakness of first-order logic, not evidence against objective mathematical truth. This connects back to his Platonism. Mathematical concepts are grasped intuitively, and this intuition fixes a unique intended interpretation, even when formal axioms underdetermine it. The axioms are attempts to describe the concepts, and we revise axioms when they fail to capture what we intend. But the concepts themselves, and the structures they pick out, are objective. Let me conclude this part by reflecting on Gödel's legacy in set theory. His work on constructibility, the continuum hypothesis, and large cardinals reshaped the field. The techniques he developed, inner models, consistency proofs, relative consistency, became standard tools. His philosophical vision of seeking new axioms to settle independent questions guides contemporary research. Yet the problems he cared most about remain unsolved. The continuum hypothesis is still independent of standard axioms plus large cardinals. No consensus exists on what axioms should extend ZF. The philosophical questions about mathematical truth and the nature of sets are as contested as ever. Some see this as failure. Gödel's program has not delivered what he hoped. Others see it as evidence of the depth and difficulty of the questions he raised. Set theory after Gödel has become a rich, sophisticated field, exploring the upper reaches of infinity and the foundations of mathematics. His incompleteness theorems and constructibility results showed that simple answers were impossible, forcing mathematicians to develop new tools and ideas. Perhaps the deepest lesson is that mathematics is inexhaustible. No matter how far we extend our axioms, independent questions will remain. The structure of mathematical reality is so rich that no finite axiomatization can capture it completely. This is not a defect, but a reflection of the infinite depth of mathematics. Gödel revealed this depth, and his work remains a foundation for anyone exploring the ultimate nature of mathematical truth. Part 4. Logic and Completeness. Before Kurt Gödel shattered mathematical certainty with incompleteness, he established something equally profound: the completeness of first-order logic. This was his doctoral dissertation in 1929, submitted when he was just 23 years old. The completeness theorem proved that logical truth and provability coincide in first-order logic. Every statement that is logically valid can be formally proven. Logic, at least, is complete. This achievement alone would have secured Gödel's place in the history of logic. But the completeness theorem is also where Gödel first developed the techniques that would lead to incompleteness. Understanding what he proved, why it matters, and how it relates to his later work reveals the profound unity of his logical investigations. The problem Gödel addressed concerned the relationship between semantics and syntax in logic. Semantics deals with meaning and truth. When is a logical formula true? Syntax deals with formal proof. When can a formula be derived from axioms using rules of inference? David Hilbert and Wilhelm Ackermann had formulated a system of axioms and rules for first-order logic in 1928, and they asked whether this system was complete, whether every valid formula could be proven. First-order logic is the logic of quantifiers and predicates. It allows statements like, for all x, if x is human, then x is mortal, or there exists an x such that x is prime and x is greater than 2. These statements use quantifiers, for all, there exists, ranging over a domain of objects, plus predicates expressing properties of those objects. A formula is logically valid if it is true in all possible interpretations. For instance, the formula, for all x, either p of x or not p of x is valid because no matter what domain you consider, and no matter what property p represents, the statement is true. Every object either has property p or lacks it. This is the law of excluded middle applied to predicates. A formula is provable if it can be derived from logical axioms using rules of inference. Start with basic logical truths like A implies A, and apply rules like modus ponens. If you have proved A and proved A implies B, you can derive B. To generate new theorems, the question is whether these two notions coincide. Is every valid formula provable? This is what completeness asks. Gödel proved the answer is yes. He showed that the Hilbert-Ackermann axiom system for first-order logic is complete. Every logically valid formula is provable. The proof was ingenious and involved constructing, for any unprovable formula, an interpretation where the formula is false. This showed that unprovable formulas are not valid, hence provable formulas coincide with valid ones. The technique Gödel used anticipated later model-theoretic methods. He showed how to build models of logical theories systematically, checking whether formulas hold in those models. This gave birth to model theory as a branch of logic. The interplay between syntax and semantics became a central theme in 20th century logic, largely due to Gödel's completeness theorem. But why does completeness matter? What hangs on whether valid formulas are provable? First, completeness establishes that formal proof systems capture all of logical truth. If you want to know whether a statement is logically valid, you can try to find a proof. If it is valid, a proof exists. This vindicates the idea that logical reasoning can be formalized without losing anything essential. Everything inferable by pure logic can be inferred by mechanical rules. Second, completeness implies that consistency and satisfiability are equivalent. A set of axioms is consistent. It does not prove contradictions. If and only if those axioms have a model, an interpretation where they are all true. This gives a powerful tool for showing consistency. To prove a theory is consistent, find a model of it. Third, completeness leads to the compactness theorem, which says that if every finite subset of an infinite set of axioms has a model, then the whole infinite set has a model. This has applications throughout mathematics, allowing constructions of exotic structures and proofs of existence results. Fourth, and philosophically most important, completeness shows the power and limits of first-order logic. First-order logic is strong enough to formalize vast amounts of mathematics. Nearly all mathematical proofs can be recast in first-order logic. Yet it is complete, meaning it is in some sense maximally powerful without becoming undecidable or incomplete. This contrasts sharply with second-order logic. Second-order logic allows quantification over properties and sets, not just individuals. You can say, for every property P, if P holds of 0 and P is hereditary, then P holds of all natural numbers. This is the second-order formulation of mathematical induction. Second-order logic is more expressive than first-order logic, but it is incomplete. There are valid formulas in second-order logic that are not provable, and there is no effective way to list all valid second-order formulas. Gödel was aware of this contrast. First-order logic strikes a balance between expressiveness and tractability. It is weak enough that truth and proof coincide, strong enough to formalize most of mathematics. But it is not strong enough to categorically characterize structures like the natural numbers. First-order arithmetic has non-standard models with infinite numbers. Second-order arithmetic pins down the standard model uniquely, but at the cost of incompleteness. This suggests something about the nature of mathematical concepts. Fully capturing them requires resources beyond first-order logic, but extending logic to second-order or higher-order systems brings incompleteness. We face a trade-off: completeness or categoricity, but not both. Gödel's philosophical interpretation was that mathematical concepts have a richness that exceeds any fixed logical formalism. The concept of natural number, for instance, determines a unique structure, the standard natural numbers. But no first-order axioms can pin down this structure uniquely. We need second-order axioms, but then we lose completeness. This shows that mathematical understanding involves something beyond formal logic, intuitive grasp of concepts that guides interpretation. Let me turn now to another aspect of Gödel's work in logic, his Dialectica interpretation of arithmetic. This work, published in 1958, addressed the foundations of arithmetic from a proof-theoretic perspective. It was part of Gödel's engagement with Hilbert's program and with intuitionism, though Gödel ultimately did not endorse either approach. Hilbert's program aimed to prove the consistency of mathematics using only finitary, constructive methods. The idea was to treat mathematics as a formal system and show metamathematically that this system never proves contradictions. This proof should use only methods that even skeptics about infinity would accept. Finite combinatorial reasoning about concrete symbols. Gödel's second incompleteness theorem devastated this program. Arithmetic cannot prove its own consistency using only its own methods. To prove arithmetic is consistent, you need stronger assumptions than arithmetic itself provides. This seemed to show that Hilbert's program was impossible. But Hilbert's program had another aspect: reducing classical mathematics to intuitionistic or constructive mathematics. Intuitionism, developed by L. E. J. Brouwer, rejects the law of excluded middle and other classical logical principles. Intuitionists accept only constructive proofs. To prove something exists, you must construct it. To prove a disjunction, A or B, you must prove A or prove B. Classical logic is more liberal, allowing indirect proofs and non-constructive arguments. Gödel investigated whether classical arithmetic could be interpreted in intuitionistic arithmetic. Could you translate classical proofs into constructive proofs, showing that anything provable classically is also provable constructively? This would be a kind of consistency proof. If intuitionistic arithmetic is consistent, so is classical arithmetic. The Dialectica interpretation accomplished this, but in a subtle way. Gödel showed how to interpret classical arithmetic in a system called System T, which is a constructive system with primitive recursive functionals. Every theorem of classical arithmetic translates into a theorem of System T. This established that classical arithmetic is consistent relative to System T. But System T is not weak. It is stronger in some respects than intuitionistic arithmetic. So the interpretation does not quite show that classical methods add nothing to constructive methods. Rather, it clarifies what additional assumptions are needed to justify classical reasoning. Philosophically, Gödel did not endorse intuitionism. He thought constructivism was too restrictive. Mathematics should not be limited to what we can explicitly construct. The classical mathematician's freedom to assert existence without construction reflects objective facts about mathematical reality. We can prove that certain structures exist, even when we cannot construct them explicitly. Yet Gödel respected intuitionism as a coherent position and wanted to understand it. The Dialectica interpretation was part of this investigation. It showed that classical and intuitionistic arithmetic are related in precise ways, even though they embody different philosophies of mathematics. Gödel also worked on intuitionistic logic itself. In 1932, he proved that intuitionistic propositional logic is not finitely many-valued. This refuted an attempt to give intuitionistic logic a simple semantics using finitely many truth values. Intuitionistic logic, if it has any truth value semantics, must use infinitely many values or some more complex structure. This work led to what is now called Gödel-Dummett logic, an intermediate system between intuitionistic and classical logic. It is weaker than classical logic, but stronger than intuitionistic logic. Gödel did not develop this system extensively, but it has become important in modern logic for understanding the space of possible logical systems. One philosophical issue these investigations raise concerns the status of logic itself. Is there a single correct logic, or are there multiple legitimate logical systems suited to different purposes? Classical logic allows the law of excluded middle. Every statement is either true or false. Intuitionistic logic rejects this for statements involving infinity or non-constructive existence. Which is right? Gödel believed classical logic is correct for reasoning about an objective mathematical reality. The continuum hypothesis, for instance, is either true or false, even though we do not know which. Intuitionistic logic reflects epistemological constraints, what we can know or construct, rather than ontological facts. It is appropriate for certain foundational investigations, but does not capture mathematical truth. This position is controversial. Many philosophers argue that logic should be about inference patterns, not metaphysics. Different logics are tools for different purposes, with no single correct logic. Gödel would have disagreed. He thought logic tracks objective truth, and that classical logic does this correctly for mathematics. Let me discuss one more area where Gödel made contributions: proof theory and ordinal analysis. Proof theory studies the structure of proofs themselves, treating them as mathematical objects. Ordinal analysis assigns ordinal numbers to formal theories, measuring their proof-theoretic strength. Gödel did not develop proof theory as extensively as he did model theory, but he engaged with it in connection with Hilbert's program. Gensen proved the consistency of arithmetic in 1936 using transfinite induction up to epsilon 0, an ordinal number. This was after Gödel's incompleteness theorem showed that arithmetic cannot prove its own consistency. Gensen's result did not contradict incompleteness because he used methods not formalizable within arithmetic itself, namely transfinite induction up to epsilon 0. Gödel recognized the significance of this. It showed that stronger proof-theoretic methods could establish consistency of weaker systems. This suggested a hierarchy of proof-theoretic strength, with each level capable of proving the consistency of levels below. This hierarchy became central to modern proof theory. The philosophical lesson is that mathematical knowledge has structure. We do not need absolute foundations that prove their own consistency. Instead, we can justify weaker systems using stronger ones, and justify stronger systems using still stronger ones. As long as this hierarchy does not circle back on itself, which incompleteness shows it cannot, we avoid vicious circularity. Gödel also recognized that proof-theoretic strength and set-theoretic strength need not coincide. A theory might be proof-theoretically weak, but set-theoretically strong, or vice versa. Different measures of strength capture different aspects of the theory's power. This pluralism about strength was typical of Gödel's sophisticated understanding of foundations. Now let me address how the completeness theorem and incompleteness theorems fit together in Gödel's overall vision of logic and mathematics. At first glance, they seem contradictory. Completeness says logic captures all valid reasoning. Incompleteness says arithmetic has truths beyond what axioms can prove. How can both be true? The resolution, as we have seen, is that logic and mathematics are different. Pure logic, reasoning involving only logical vocabulary, is complete. But mathematics involves specific concepts like number and set that have content beyond logic. Once you introduce mathematical axioms, incompleteness appears. This shows that mathematics is not reducible to logic. Frege and Russell tried to reduce arithmetic to logic, showing that mathematical truths are ultimately logical truths. Gödel's theorems undermine this. Logic is complete, arithmetic is not. Therefore, arithmetic cannot be logic. Mathematics has its own subject matter that logic alone cannot capture. From Gödel's Platonist perspective, this makes perfect sense. Mathematical concepts pick out objective structures, the natural numbers, the real numbers, the universe of sets. These structures have properties that go beyond what any formal system can exhaust. Logic provides tools for reasoning, but mathematics requires intuitive understanding of its specific concepts. The completeness and incompleteness theorems together also reveal something about the nature of proof. Proof, in the logical sense, formal derivation from axioms, is complete for pure logic, but incomplete for mathematics. Proof in the intuitive sense, convincing reasoning that establishes truth, extends beyond formal derivation. When we recognize a Gödel sentence as true, we are using informal proof that transcends the formal system. Gödel believed mathematics always involves this informal element. We can never eliminate intuitive understanding in favor of purely mechanical reasoning. Formalization is useful for clarity and rigor, but it does not replace mathematical insight. This is why mathematical creativity is indispensable. Discovering new theorems requires recognizing patterns and relationships that formal systems do not automatically generate. Some philosophers and computer scientists have resisted this conclusion. They want to mechanize mathematics completely, reducing proof to algorithm. Automated theorem provers have made impressive progress, finding proofs of complex theorems. But they operate within fixed formal systems and cannot generate new axioms or recognize when systems are inadequate. They lack the intuitive understanding that guides human mathematicians. Gödel would have predicted this limitation. Intuition cannot be algorithmatized because it involves grasping concepts that transcend any fixed rules. This does not mean intuition is mysterious or supernatural. It is a cognitive capacity for recognizing conceptual relationships, but it is not reducible to following formal procedures. Let me conclude this part by considering Gödel's broader impact on logic as a discipline. Before Gödel, logic was primarily philosophical, analyzing arguments and clarifying reasoning. After Gödel, logic became mathematical, studying formal systems with mathematical techniques. This transformation was largely due to Gödel's work. The completeness theorem inaugurated model theory. The incompleteness theorems inaugurated metamathematics and the study of formal systems as mathematical objects. The techniques Gödel developed, arithmetization, Gödel numbering, diagonal arguments, inner models, became fundamental tools. Modern logic is unthinkable without them. Gödel also showed that logic and mathematics interpenetrate in profound ways. Logical results have mathematical implications. Mathematical results have logical significance. The boundaries between logic, foundations, and mathematics blurred. This interdisciplinary character defines contemporary logic and foundations. Yet Gödel remained philosophically engaged with logic in ways that many modern logicians are not. He cared deeply about what logical results mean for mathematics, truth, and knowledge. The completeness theorem was not just a technical achievement, but a statement about the power of formal reasoning. The incompleteness theorems were not just limitations on formal systems, but revelations about the nature of mathematical truth. This combination of technical brilliance and philosophical depth distinguishes Gödel from most logicians. He used mathematics to address philosophical questions and allowed philosophical considerations to guide his mathematics. His work in logic exemplifies how technical work and conceptual reflection can illuminate each other. Understanding logic requires both formal mastery and philosophical sensitivity, a lesson Gödel embodied throughout his career. Part 5. Physics, Relativity, and Cosmology. In 1942, Kurt Gödel attended a lecture series on cosmology at the Institute for Advanced Study in Princeton. There he met Albert Einstein. The two became close friends, taking daily walks together and discussing physics, philosophy, and mathematics. This friendship between the greatest logician and the greatest physicist of the 20th century produced one of the most remarkable collaborations in intellectual history. Gödel began studying Einstein's theory of general relativity seriously in the mid-1940s. By 1949, he had discovered something stunning, an exact solution to Einstein's field equations describing a rotating universe. More extraordinarily, this universe contained closed, time-like curves, paths through space-time that loop back to their starting point. In Gödel's universe, time travel to the past is physically possible. This was not science fiction speculation. It was rigorous mathematics applied to Einstein's fundamental equations of gravity and space-time. Gödel proved that the laws of general relativity, which describe our actual universe, allow for universes where causality breaks down and time becomes circular. The implications shook Einstein and continue to reverberate through physics and philosophy. Let me explain what Gödel discovered and why it matters, starting with the basics of general relativity. Einstein's theory revolutionized our understanding of space, time, and gravity. According to general relativity, space-time is not a fixed background stage where events occur. It is a dynamic entity that curves in response to matter and energy. What we experience as gravity is the curvature of space-time caused by massive objects. The Einstein field equations relate the curvature of space-time to the distribution of matter and energy. Given some arrangement of matter, these equations determine how space-time curves. Conversely, given the space-time geometry, the equations constrain what matter distributions are compatible with it. A solution to Einstein's equations is a specific space-time geometry, together with a matter distribution satisfying the field equations. The Schwarzschild solution describes space-time around a spherical mass like a star. The Friedmann-Lemaitre Robertson-Walker solutions describe expanding or contracting universes, forming the basis of modern cosmology. Each solution is a possible universe according to general relativity. Gödel found a new solution, a universe filled with a perfect fluid of dust representing idealized galaxies, rotating as a whole rather than expanding. The geometry of this universe has remarkable properties. It is homogeneous. Every point looks like every other point, and it has a preferred axis of rotation, though not a center. From any point, an observer would see the rest of the universe rotating around that point. The technical details involve writing down the metric, a mathematical description of distances and time intervals in space-time, and showing it satisfies Einstein's equations for an appropriate matter distribution. Gödel's metric is elegant and symmetric, exhibiting sophisticated mathematical structure. But the physical interpretation is where things get strange. In Gödel's universe, there are closed time-like curves, paths an observer could follow through space-time that return to their starting point in space and time. You could board a rocket, accelerate in a certain direction, travel for a long time, and return to your starting point before you left. You would encounter your younger self. How is this possible? The key is that in general relativity, the geometry of space-time determines which paths are time-like, paths that observers moving slower than light can follow. In ordinary space-time, all time-like paths extend infinitely into the past and future. But in Gödel's rotating universe, the cumulative effects of rotation and space-time curvature cause time-like paths to close in on themselves. Think of it this way. Imagine space-time as a fabric that can be twisted. In flat space-time, no amount of traveling brings you back to your own past. But in Gödel's universe, the rotation twists the fabric of space-time so severely that the future direction eventually curves back to meet the past. Following a straight path through this twisted space-time, you loop back to your starting point. The philosophical implications hit Einstein hard. He had spent decades convinced that time is relative, but that causality is absolute. Events have a definite order. Causes precede effects. The possibility of closed time-like curves threaten this. If you can travel to your own past, paradoxes arise. You could prevent your own birth, kill your grandfather before your parent was born, or create logical contradictions. Gödel was aware of these paradoxes, but not troubled by them. He saw closed time-like curves as evidence that time is not what we ordinarily think. The intuitive concept of time as a one-way flow from past through present to future does not correspond to anything in the objective structure of space-time. Time, in this sense, is ideal, not a feature of reality itself, but a subjective phenomenon of consciousness. This conclusion connected to Gödel's engagement with Kantian and idealist philosophy, which I will explore in the next part. For now, note that Gödel's argument was not just that time travel produces paradoxes. Rather, he argued that the very existence of closed time-like curves in a solution to Einstein's equations shows that time as ordinarily conceived does not exist in the physical world. His reasoning went like this. If Einstein's equations allow universes with closed time-like curves, and if those equations correctly describe the structure of space-time, then the possibility of such universes reveals something about the nature of time in all universes, including ours. Specifically, it shows that there is no objective global time, no way to divide space-time into a sequence of now moments that all observers would agree on. In ordinary relativistic spacetimes without closed curves, you can define a global time function that increases monotonically along all time-like paths. Events can be ordered as earlier and later in a way consistent across the entire universe. But in Gödel's universe, no such function exists. Time is local and relative to a degree that destroys any objective temporal order. Critics objected immediately. Our universe does not rotate like Gödel's universe. Astronomical observations show no large-scale rotation, so Gödel's solution is physically irrelevant, a mathematical curiosity allowed by Einstein's equations but not realized in nature. Gödel anticipated this objection and had a reply. The argument is not that our universe is a Gödel universe. It is that the physical laws describing our universe, Einstein's equations, permit Gödel universes. This possibility reveals something about the laws themselves, and therefore about all universes governed by those laws. Think of an analogy. Newtonian mechanics allows frictionless planes and perfectly elastic collisions, neither of which exists in nature. But studying these idealized cases reveals features of Newtonian mechanics relevant to actual systems. Similarly, studying Gödel's rotating universe reveals features of general relativity relevant to understanding time in any relativistic universe. The feature Gödel thought he had revealed is that general relativity provides no support for an objective flow of time. The theory describes space-time structure, but does not privilege any particular notion of past, present, and future. Time is not built into the fabric of reality according to general relativity. It emerges from our perspective as observers moving through space-time. This interpretation remains controversial. Many physicists and philosophers think Gödel overreached. Just because a theory allows bizarre solutions does not mean those solutions tell us about the actual world. General relativity also allows wormholes and naked singularities, but we do not conclude that spacetime is therefore riddled with wormholes or that singularities are visible. Moreover, subsequent work has shown that not all rotating universes have closed time-like curves. Some models exhibit rotation without allowing time travel. This weakens Gödel's claim that rotation plus general relativity implies temporal ideality. Yet Gödel's work stimulated immense interest in the causal structure of spacetime. Physicists began systematically studying which spacetime geometries allow closed time-like curves, under what conditions they arise, and whether they can be created artificially. This led to investigations of chronology protection, hypothetical mechanisms that prevent closed time-like curves from forming. Stephen Hawking proposed a chronology protection conjecture. The laws of physics prevent time travel to the past. Whenever conditions approach those needed for closed time-like curves, quantum effects intervene to prevent them. This remains unproven, and some physicists doubt it. But the debate stems directly from Gödel's discovery that classical general relativity allows time travel. Another legacy of Gödel's cosmological work is the realization that the global structure of spacetime matters. Early work in relativity focused on local properties, curvature at a point, trajectories of particles, field equations. Gödel showed that global topology, how spacetime connects to itself over large scales, has physical significance. This global perspective became central to modern cosmology and the study of black holes. Let me describe the technical features of Gödel's universe more precisely. The spacetime is homogeneous, meaning it looks the same at every point. There is no preferred location. But it is not isotropic. It does not look the same in all directions from a given point. The rotation breaks directional symmetry. Every observer sees a preferred axis around which the universe rotates. The matter content is a perfect fluid of dust with uniform density. The pressure is zero, and the dust particles represent idealized galaxies. The fluid rotates with an angular velocity related to the density by Einstein's field equations. Balancing rotation against gravitational collapse, the universe maintains a static configuration, neither expanding nor contracting. The metric describing distances and time intervals has a specific mathematical form discovered by Gödel. In appropriate coordinates, it involves hyperbolic functions and exhibits cylindrical symmetry around the rotation axis. Calculating geodesics, paths that free-falling observers follow, reveals the closed time-like curves. They require traveling a long distance, not just circling around a small loop. One fascinating feature is that light rays in Gödel's universe also behave strangely. A flash of light emitted from a point will spread out, but due to the rotation and curvature, the light rays eventually reconverge at a later point on the rotation axis. This creates a kind of focusing effect unlike anything in ordinary cosmologies. Gödel also investigated whether his universe could represent a realistic cosmological model if modified slightly. Perhaps a rotating universe with expansion could match observations while retaining interesting causal properties. But all such attempts ran into difficulties. Rotation strong enough to produce closed curves is incompatible with the observed large-scale isotropy of the cosmic microwave background. Modern cosmology has placed increasingly tight constraints on possible rotation of the universe. Any rotation must be extremely slow, far too slow to generate closed time-like curves. so Gödel's exact solution does not describe reality. But the conceptual issues it raised remain relevant. One issue concerns the relationship between mathematics and physics. General relativity is a mathematical theory expressed through differential geometry. It makes predictions by solving equations. But the equations have many solutions, most physically unrealistic. Which solutions represent possible universes? Which are mere mathematical artifacts? Gödel's universe is an exact solution to Einstein's equations, not an approximation or limiting case. Mathematically, it is on equal footing with the Friedmann-Robertson-Walker expanding universes that describe our cosmos. Yet physically, it seems bizarre and unrealistic. What justifies distinguishing physically reasonable solutions from unreasonable ones? One answer is initial conditions and boundary conditions. Our universe began in a Big Bang with specific initial conditions. Only solutions compatible with those conditions are relevant. Gödel's universe has different initial conditions. It is static rather than expanding, rotating rather than isotropic. So it is simply not the universe we inhabit. But Gödel would have resisted this. He thought that if Einstein's equations allow a type of spacetime, that type is physically possible in a deep sense. The equations are supposed to capture the laws of gravity and spacetime structure. If closed time-like curves are consistent with those laws, then they reveal something about the nature of spacetime itself, regardless of whether our particular universe exhibits them pause. The argument goes like this. Special relativity already showed that simultaneity is relative. Two events that are simultaneous in one reference frame may not be simultaneous in another frame moving relative to the first. There is no absolute fact about whether distant events happen at the same time. This relativity of simultaneity undermines any notion of a universal present moment. General relativity deepens this problem. In curved spacetime, defining simultaneity globally becomes even more difficult. In some spacetimes, like the expanding universe we inhabit, you can define a cosmic time that gives a consistent ordering of events throughout the universe. But this ordering is not unique. It depends on how you slice spacetime into spatial hypersurfaces, and it does not correspond to any observer-independent present. Gödel's rotating universe takes this further. In a universe with closed time-like curves, you cannot define a global time function at all. There is no way to assign a time coordinate to events such that time consistently increases along all time-like paths. Any attempt to do so leads to contradictions. You would have events that are both earlier and later than themselves. Gödel argued this shows that time, in the intuitive sense of a flowing present dividing past from future, is not part of the objective structure of spacetime. Spacetime has a geometrical structure described by a metric tensor and curvature. It has causal structure, which events can influence which others, but it does not have temporal structure in the sense of an objective now, or a direction of temporal flow. If time were objective, Gödel reasoned, then Einstein's equations would not allow universes without it. The fact that those equations permit Gödel universes shows that time is not built into the laws of general relativity. And since those laws correctly describe spacetime structure, time is not part of objective physical reality. Critics immediately objected that our universe is not a Gödel universe. We observe expansion, not rotation. Our spacetime does have a well-defined cosmic time, so Gödel's argument proves at most that time is not necessary according to general relativity, not that time does not exist in the actual world. Gödel had a response, though many find it unconvincing. He argued that the possibility of timeless universes consistent with the same physical laws as our universe shows that time is not a fundamental feature of reality. If time were objective, it would have to exist in all universes governed by the laws of general relativity. The existence of even one lawful universe without time demonstrates that time is not required by the laws themselves. Think of an analogy. Suppose a physical theory allowed both universes with 3 spatial dimensions and universes with 4 spatial dimensions. This would show that the number of spatial dimensions is not determined by the fundamental laws, but by contingent boundary conditions. Similarly, if general relativity allows both temporal and timeless universes, this shows temporal structure is not fundamental. Whether this argument works is debatable. Many philosophers reject the inference from some lawful universes lack time to time is not objective in any universe. They argue that time might be objective in temporal universes, even if it is absent from timeless ones. Different solutions to Einstein's equations might have different metaphysical properties, but Gödel was drawing on a deeper philosophical conviction that the structure of physical law reveals what is metaphysically fundamental. Contingent features of particular solutions are not part of the essence of physical reality. Only features present in all solutions, or built into the laws themselves, are truly real. Since time is not among these universal features, it is ideal. This connects to Gödel's rationalism. He believed reason can determine the fundamental nature of reality by examining physical laws and mathematical structures. Empirical investigation discovers the laws. Rational analysis of those laws reveals what exists objectively. Time fails this test. It appears in some solutions but not others, so it is not fundamental. Now let me explore Gödel's engagement with Kant more deeply. Kant was the first philosopher Gödel studied seriously, reading the Critique of Pure Reason as a teenager. Throughout his life, Gödel expressed both admiration for Kant and criticism of his errors. This ambivalent relationship reveals much about Gödel's own philosophical development. Kant distinguished phenomena, things as they appear to us, from noumena, things in themselves. Space and time belong to phenomena. They are forms through which we experience the world, not features of things in themselves. This transcendental idealism avoids skepticism about the external world because it does not deny that there is a real world independent of minds. It only denies that we know that world as it is in itself. We know it only as it appears through the forms of intuition and categories of understanding. Gödel appreciated this move. He saw Kant as recognizing both the objective existence of reality and the mind's contribution to knowledge, but he thought Kant exaggerated the divide between phenomena and noumena. Kant suggested things in themselves are unknowable. Gödel believed reason can penetrate beyond appearances to grasp objective reality, at least in mathematics and through scientific investigation. On time specifically, Gödel agreed with Kant that ordinary temporal experience does not correspond to objective reality. The flowing present is phenomenal. But Gödel thought Kant was wrong to conclude that time is purely subjective. Rather, time as studied in physics, relativistic space-time structure, is objective, even though it differs radically from intuitive time. This led Gödel to distinguish two concepts of time. Intuitive time is the time of conscious experience, the sense of now, the flow from past through present to future, the feeling that the past is fixed while the future is open. Physical time is the time of relativity theory, a coordinate in space-time, relative to reference frames, part of a four-dimensional geometrical structure. Gödel argued that intuitive time is ideal, existing only in consciousness. Physical time, or rather space-time, is real. But physical time lacks the features of intuitive time that we care about, the flowing present, the distinction between past and future, the openness of the future. So in the sense that matters for human experience, time is ideal. This twofold conception led to what might seem like paradox. Gödel was a realist about space-time. It exists objectively, but an idealist about time. The temporal features of conscious experience do not correspond to objective reality. How can both be true? The answer is that space-time has geometrical and causal structure, but not genuinely temporal structure. Events are related spatially and causally, but not temporally in the intuitive sense. When we experience events as occurring in time, we are imposing a subjective framework on objective space-time. That framework helps us navigate and understand the world, but does not reflect how things are in themselves. Gödel found support for this view in Leibniz, another philosopher he admired deeply. Leibniz was an idealist about space and time, though for different reasons than Kant. Leibniz argued that space and time are not substances or absolute containers, but relations between things. They are ways of ordering phenomena, not entities in their own right. Gödel saw Leibniz as anticipating aspects of relativity theory. Leibniz's relationalism about space and time coheres with Einstein's insight that space-time is relational structure rather than absolute background. But Gödel also recognized differences. Leibniz was an idealist about space as well as time, whereas Gödel thought space-time has objective reality. Still, Gödel felt a kinship with Leibniz's rationalism and his metaphysical system. Leibniz believed the world is fundamentally made of monads, simple substances with inner mental states. External relations and physical interactions are appearances of the underlying monadic structure. This idealism about the phenomenal world, combined with realism about monads, appealed to Gödel's temperament. Gödel spent years studying Leibniz's unpublished manuscripts, believing important ideas had been suppressed. He even thought there might have been a conspiracy to hide Leibniz's deeper philosophical insights. This interest in Leibniz influenced Gödel's own metaphysics, though he never articulated a complete system comparable to Leibniz's monadology. Another influence on Gödel's thinking about time was Edmund Husserl, the founder of Phenomenology. Gödel began studying Husserl seriously in 1959 and was deeply affected. Phenomenology studies the structures of conscious experience, including temporal experience. Husserl analyzed how consciousness synthesizes moments into a flowing temporal sequence, how we experience succession and duration. Gödel saw phenomenology as providing a systematic method for clarifying concepts, including the concept of time. By examining how temporal experience is structured, we can distinguish subjective temporal features from objective ones. This helps disentangle intuitive time from physical time. Husserl himself did not endorse idealism about time in Gödel's sense. Husserl was interested in the phenomenology of time consciousness, not in whether time is ultimately real or ideal. But Gödel thought Husserl's methods could be adapted to support temporal idealism. By clarifying the essential structures of temporal experience, phenomenology reveals that those structures belong to consciousness rather than to reality itself. This brings us to Gödel's complicated relationship with idealism more generally. He called his philosophy idealistic, yet he was a realist about mathematics and physics. How does this fit together? The key is distinguishing different forms of idealism. Metaphysical idealism says reality is fundamentally mental or spiritual. Berkeley's idealism, for instance, holds that only minds and their ideas exist. Gödel rejected this. He believed in an objective reality independent of minds, including abstract mathematical objects and physical space-time. Epistemological idealism says we cannot know things as they are in themselves, only as they appear through our conceptual frameworks. Kant's transcendental idealism is partly epistemological. Gödel rejected strong versions of this too. He thought reason can grasp objective truths, not just appearances. But Gödel endorsed a selective idealism about certain features we intuitively attribute to reality. Time, in the sense of a flowing present, is ideal. Space, in the sense of Euclidean geometry, is ideal. Real space has non-Euclidean structure. Causality, in the sense of necessary connection, is ideal. These features belong to our way of experiencing rather than to things themselves. So Gödel's idealism was limited and specific. He was an idealist about intuitive time, an realist about space-time, an idealist about phenomenal appearances, a realist about abstract structures and physical laws. This selective approach distinguished him from traditional idealists who were idealistic across the board. One philosophical problem for Gödel's view concerns the relationship between intuitive time and physical time. If our experience represents events as occurring in time, and if this representation is systematically mistaken, how did such representations evolve? Why would evolution produce minds that misrepresent temporal structure? Gödel did not address this question explicitly, but a response might go like this. Evolution shaped minds to navigate local space-time structure effectively. Local relativistic space-time has features that approximate intuitive time. Events at nearby locations have definite temporal order. Causes precede effects locally. So intuitive time is an approximation, useful for survival, even though it breaks down globally, or in extreme situations like Gödel universes. This would make intuitive time analogous to Euclidean geometry. Locally, space seems Euclidean, and this approximation is good enough for everyday purposes. Only when we consider large scales or strong gravitational fields does non-Euclidean structure become apparent. Similarly, intuitive time works locally but fails globally. Another problem concerns the phenomenology of time. Even if time is ideal, we still experience it. The flow of time feels real. Accounting for this experience is philosophically important. If time does not flow objectively, why does it seem to flow subjectively? This is the question of temporal experience, or time consciousness, which philosophers and neuroscientists continue to debate. How does the brain create the sense of temporal flow? Why do we experience a distinguished present moment? How do we perceive succession and duration? These questions remain largely unanswered. Gödel did not solve them, but he thought clarifying the distinction between intuitive and physical time was a necessary first step. Once we recognize that physical time lacks the structure of intuitive time, we can investigate how minds construct temporal experience. The experience is real as experience, even if it does not correspond to objective temporal structure. Let me conclude this part by considering whether Gödel's argument for the ideality of time succeeds. This remains hotly debated among philosophers of physics and metaphysicians. Supporters argue that relativity theory genuinely undermines the objectivity of temporal flow and the present moment. Space-time is a four-dimensional block where all events exist tenselessly. The distinction between past, present, and future is not objective but reflects our temporal perspective. Gödel's rotating universes make this even clearer by showing that some lawful spacetimes have no consistent global time. Critics respond in various ways. Some deny that relativity theory requires abandoning objective time. Perhaps the present is relative to reference frames, but still objective within each frame. Or perhaps there is a preferred reference frame defining absolute simultaneity, even if relativity does not pick it out. Others argue that the mere possibility of timeless universes does not show time is ideal in our universe. Actuality matters more than possibility. Still others accept that physical time is not like intuitive time, but deny this makes time ideal. Physical time is real, just different from what we expected. Revising our concept of time to match relativistic spacetime is progress, not evidence that time is illusory. My assessment is that Gödel's argument shows something important but does not decisively establish idealism. It shows that intuitive time does not map neatly onto relativistic spacetime. It shows that the flowing present and absolute simultaneity are not part of fundamental physics. But whether this makes time ideal or merely shows that our intuitions were wrong is a further question that depends on how one defines ideality and objectivity. What is undeniable is that Gödel's work on relativistic cosmology and his philosophical reflections on time deeply influenced debates in philosophy of physics. He showed that studying exact solutions to Einstein's equations can reveal conceptual problems and philosophical implications. He demonstrated that mathematical physics and metaphysics can inform each other productively. And he left a puzzle for philosophy. How should we understand the relationship between our temporal experience and the structure of physical spacetime? This puzzle remains unsolved, a testament to the depth and difficulty of the questions Gödel raised by bringing logic, mathematics, physics, and philosophy together in his investigation of time's reality. Part 7. The Ontological Argument for God. In 1970, Kurt Gödel believed he was dying. For years he had worked privately on a logical proof of God's existence, refining it in notebooks he showed to no one. Now, thinking the end was near, he allowed his colleague Dana Scott to copy out the proof. Gödel made Scott promise not to publish it widely. He feared, he later told his friend Oscar Morgenstern, that people would think he actually believed in God, when he was merely pursuing a logical investigation. This statement is odd and revealing. Gödel did believe in God. He read the Bible regularly, held theological views, and told friends he was convinced of an afterlife. So why the pretense of detachment? Perhaps because he recognized how strange it would seem for a rigorous logician to present a proof of God's existence. Or perhaps because the proof itself was so abstract and formal that calling it religious seemed misleading. Or perhaps because he understood the proof had limitations he could not overcome. Gödel never published the Ontological Argument during his lifetime. It appeared only after his death in 1978, when his papers were examined and Scott's version was compared with manuscripts found among Gödel's writings. Since then, philosophers and logicians have analyzed, criticized, and defended it. Computer scientists have even verified its logical validity using automated theorem provers. But whether it proves anything about God remains deeply controversial. To understand Gödel's proof, we need to grasp the ontological tradition it emerges from and the specific logical machinery he employed. Ontological arguments attempt to prove God's existence from the concept of God alone, using pure reason without appealing to empirical evidence. The idea goes back to Anselm of Canterbury in the 11th century. Anselm argued that God is by definition the greatest conceivable being. Now, suppose God exists only in our minds, not in reality. Then we could conceive of something greater, a being with all of God's perfections that also exists in reality. But this contradicts the definition of God as the greatest conceivable being. Therefore, God must exist in reality as well as in our minds. This argument struck many as too clever to be sound. How can you prove something exists just by analyzing concepts? Existence is not a property like wisdom or power that you can build into a definition. Critics from Anselm's contemporary, Gaunilo, to Kant centuries later, rejected ontological arguments as sophistical tricks. But the arguments kept reappearing in new forms. Descartes argued that existence belongs to God's essence, just as three angles belong to a triangle's essence. You cannot coherently conceive of God without existence, any more than you can conceive a triangle without three angles. Leibniz refined this by noting that the argument only works if God is possible, if the concept of God is coherent. So Leibniz attempted to prove that God's existence is possible, which, together with the Cartesian argument, would yield that God necessarily exists. Gödel studied Leibniz's version intensively and developed his own proof building on it. He used modal logic, the logic of necessity and possibility, and he worked with the concept of positive properties rather than perfections. The proof is technical, involving axioms and definitions from which conclusions are derived rigorously. Let me explain it step by step, translating the formal logic into philosophical language. Gödel starts with the concept of a positive property. He does not define what makes a property positive, treating it as a primitive notion. Intuitively, positive properties are those that enhance or perfect whatever has them. Being omniscient, being omnipotent, being perfectly good, these are positive. Their negations, being ignorant, being powerless, being evil, are negative. Axiom 1 says that if a property is positive and that property necessarily implies another property, then the second property is also positive. Positiveness is closed under necessary implication. If being omniscient is positive and omniscience implies knowledge, then knowledge is positive. Axiom 2 says that for any property, either it or its negation is positive, but not both. Every property is either positive or negative. There is no neutral ground. From these axioms, Gödel proves Theorem 1. If a property is positive, then it is possibly instantiated. There could be something with that property. The proof works by contradiction. If a positive property were impossible, it would vacuously imply every property, including negative properties. But then negative properties would be positive, violating axiom 2. So positive properties must be possible. Now Gödel defines God. A being is God-like if it has every positive property. This is definition 1. God is not defined as a creator or judge or person, but as the instantiation of all positive properties. Axiom 3 says that being God-like is itself a positive property. This is a substantial assumption. It claims that having all positive properties is better than having only some. From Axiom 3 and Theorem 1, Gödel derives Theorem 2. It is possible that God exists. There could be a godlike being. This follows because being godlike is positive, and positive properties are possibly instantiated. So far, the proof establishes only that God's existence is possible, not that God actually exists. The next stage moves from possibility to necessity. Gödel introduces the concept of essence. A property is the essence of an individual if that individual has the property, and the property necessarily implies every other property the individual has. An essence captures everything essential about what something is. He then proves Theorem 3. If a being is godlike, then being godlike is its essence. This means God's nature is captured entirely by having all positive properties. Nothing about God is accidental or contingent beyond this. Now comes Axiom 4. If a property is positive, then it is necessarily positive. Positiveness does not vary across possible worlds. What is positive in all possible circumstances. Gödel defines necessary existence. An individual necessarily exists if every essence of that individual is necessarily instantiated. Necessary existence means existing in all possible worlds, not just the actual world. Axiom 5 says that necessary existence is a positive property. This is the most controversial axiom. It claims that existing necessarily is better than existing contingently. A being that could fail to exist is less perfect than one that must exist. From Axiom 5 and the earlier results, Gödel proves Theorem 4. God necessarily exists. The argument is roughly this. Being godlike is an essence of God. Necessary existence is a positive property. Since God has all positive properties, God has necessary existence. Therefore, God's essence is necessarily instantiated. Therefore, God exists in all possible worlds, including the actual world. This is a valid logical argument. If you accept the axioms and definitions, the conclusion follows. Computer verification has confirmed this. The proof is technically correct, but does it establish that God exists? Nearly everyone who examines the proof questions the axioms. Why should we believe Axiom 2, that every property is either positive or negative with no neutral ground? Why should we believe Axiom 5, that necessary existence is positive? These assumptions are not self-evident. They require justification that Gödel did not provide. The most serious objection concerns modal collapse. Jordan Howard Sobel proved that Gödel's axioms imply that if any proposition is true, it is necessarily true. There are no contingent truths. Everything that happens must happen. This is an absurd consequence that most philosophers reject. If Gödel's axioms lead to modal collapse, they must be false. Gödel was aware of potential problems, but did not address modal collapse explicitly. Some defenders of the proof have modified the axioms to avoid collapse while retaining the conclusion. Others argue that modal collapse is not as problematic as it seems, but most philosophers see it as a decisive refutation. Another objection, raised by Graham Oppy and others, is that the axioms prove too much. If Gödel's reasoning works, similar arguments could establish the necessary existence of all sorts of entities, a maximally evil being, an almost God lacking one property, or other bizarre objects. The proof seems to show not that God exists, but that the axioms are defective. There is also the question of what the proof establishes, even if valid. The godlike being in Gödel's proof is defined purely by having all positive properties, but this seems distant from the God of religious tradition. Does the godlike being care about humans? Does it answer prayers, perform miracles, judge the living and the dead? None of this follows from having all positive properties. Gödel's God might be an impersonal principle or an abstract perfection, rather than a personal deity. Gödel himself recognized this gap. He told Morgenstern that the proof was a logical exercise, not a religious argument. Whether the godlike being whose existence is proven corresponds to the God of Christianity or Judaism or Islam is a further question. The proof shows at most that something with maximal perfections exists necessarily. Identifying this with the God of religious belief requires additional argument. Why, then, did Gödel work on the proof? Several motivations seem to have converged. First, intellectual curiosity. Ontological arguments are philosophically fascinating puzzles. Showing that rigorous modal logic could formalize and extend them was an achievement in itself. Second, his rationalism. Gödel believed pure reason could reach metaphysical truths. An ontological proof, if successful, would vindicate this conviction. Third, his theological interests. Though he kept them private, Gödel held religious beliefs. Proving God's existence through logic would support those beliefs. But Gödel also seems to have had doubts. He refined the proof repeatedly over decades, suggesting he found flaws or limitations. He never published it, suggesting he was not fully satisfied. And his statement to Morgenstern reveals ambivalence about how the proof should be understood. One interpretation is that Gödel saw the proof as showing what follows from certain assumptions about positiveness and perfection. If you grant that perfections are positive, that God has all perfections, and that necessary existence is a perfection, then God exists necessarily. This conditional claim is what the logic establishes. Whether the antecedent is true requires philosophical argument beyond the formal proof. This would make the ontological argument a tool for clarifying concepts rather than a demonstration. It shows what commitments are entailed by believing in a maximally perfect being. It reveals the structure of the concept of God, but it does not prove God exists unless you already accept the axioms. Contemporary work on the ontological argument has taken various directions. Some philosophers use modal logic to explore different versions of the argument with modified axioms. Others use possible world semantics to clarify what necessary existence means. Still others reject ontological arguments entirely, following Kant in denying that existence is a property or perfection at all. The debate also connects to broader questions in metaphysics and logic. What is existence? Is it a property like others, or is it somehow special? What makes properties positive or perfections? Can we reason from concepts to reality, or must all existence claims be grounded in experience? These questions transcend the specific ontological argument, touching fundamental issues in philosophy. Gödel's version remains notable for its logical rigor and its use of higher-order modal logic. Whether or not it succeeds as a proof, it demonstrates how formal methods can be applied to traditional philosophical problems. It shows the power of symbolic logic to make arguments precise and checkable, and it illustrates both the promise and the limits of trying to prove metaphysical conclusions through pure reason. One more aspect deserves attention: Gödel's 14-point philosophical program found among his papers. This list outlines his core convictions, many of which connect to his work on the ontological proof. Point 4 says there are other worlds and rational beings of a different and higher kind. Point 5 says the world we live in is not the only one in which we shall live or have lived. Point 13 says there is a scientific, exact philosophy and theology dealing with concepts of the highest abstractness, and this is highly fruitful for science. These points reveal a metaphysical vision going far beyond mathematics and logic. Gödel believed in a reality richer than the physical universe, populated by non-physical intelligences, structured by principles reason can grasp. The ontological proof fit into this larger picture. God exists as the supreme being in this richer metaphysical reality, knowable through rational insight. Whether this vision is compelling depends on one's philosophical temperament. Materialists and naturalists reject it as baseless speculation. Theists and idealists may find it congenial, but still question whether reason alone can establish such sweeping claims. Gödel himself seemed torn between confidence in reason's power and recognition of its limits. The ontological argument represents Gödel at his most ambitious and most vulnerable. Ambitious because he attempted to prove the most momentous claim possible, that God exists, using only logic and definitions. Vulnerable because the proof relies on contestable assumptions and leads to problematic consequences. It stands as a monument to rationalist aspiration, a reminder of both the power and the peril of trying to deduce reality from concepts. Part 8. Phenomenology and Husserl. In 1959, at age 53, Kurt Gödel underwent a philosophical conversion. He began reading Edmund Husserl's Phenomenology and became convinced he had found the right approach to philosophy. For the next 2 decades, Husserl's ideas profoundly influenced his thinking about mathematics, logic, and the nature of philosophical inquiry. This turn to phenomenology was one of the most important developments in Gödel's intellectual life, though its significance is often overlooked. Phenomenology is the study of conscious experience and how consciousness is structured. Founded by Husserl in the early 20th century, it examines how we perceive objects, how we grasp meanings, how temporal experience is organized, and how intentionality, the directedness of consciousness toward objects, makes knowledge possible. Phenomenology aims to describe the essential structures of experience through careful introspection and conceptual analysis. What attracted Gödel to this approach? He had struggled for years to justify mathematical Platonism, to explain how we can know about abstract objects, and to articulate a systematic philosophical method. Phenomenology seemed to offer solutions. It provided a technique for clarifying concepts through examining how consciousness grasps them. It took intuition seriously as a legitimate source of knowledge, and it promised to be rigorous, a strict science in Husserl's words, rather than speculative metaphysics. Gödel described phenomenology as the only philosophy that really did justice to the core of Kant's thought. Husserl had studied Kant carefully and saw his own project as completing what Kant began. Kant argued that we cannot know things in themselves, only phenomena shaped by our forms of intuition and categories of understanding. Husserl accepted that consciousness structures experience, but thought we could investigate this structuring systematically. By examining how consciousness operates, we could clarify concepts and understand the conditions for knowledge. But Husserl avoided Kant's skeptical conclusion that things in themselves are unknowable. Phenomenology brackets questions about external reality. It neither affirms nor denies that objects exist independently, and focuses on how things appear to consciousness. This bracketing, called the phenomenological reduction, or epoche, allows pure description of experiential structures without metaphysical commitments. Gödel appreciated this method because it avoided both naive realism and radical skepticism. It neither assumes uncritically that we directly perceive external reality, nor concludes that we cannot know anything beyond subjective experience. Instead, it investigates the correlation between consciousness and its objects, clarifying how meaning emerges and how knowledge is structured. For mathematics, this approach was promising. Mathematical intuition, the direct grasping of mathematical concepts and their properties, could be studied phenomenologically. By examining how mathematical consciousness works, how we apprehend concepts like number or set, we could understand what justifies mathematical knowledge. This would vindicate mathematical Platonism without requiring mysterious causal interactions between minds and abstract objects. Gödel also saw phenomenology as providing the systematic philosophical method he had sought. Philosophy should be rigorous, like mathematics, progressing through careful analysis rather than speculation. Husserl's phenomenology claimed to be such a rigorous method. It involved disciplined examination of consciousness, systematic description of essential structures, and step-by-step clarification of concepts. In a draft lecture from 1961, Gödel wrote that phenomenology is not a science in the same sense as other sciences. Rather, it is a procedure or technique that should produce in us a new state of consciousness in which we describe in detail the basic concepts we use in our thought, or grasp other basic concepts hitherto unknown to us. This is striking. Gödel saw phenomenology as transformative, a method that changes how we think by making us aware of conceptual structures we normally take for granted. He also connected phenomenology to mathematics directly. Mathematical intuition is not a mysterious faculty, but a mode of consciousness directed toward abstract objects and concepts. By clarifying how this directedness works, phenomenology could explain mathematical knowledge. The objects of mathematical intuition are not causally active entities in space and time. They are ideal objects, structures of meaning given to consciousness. But they are objective, in the sense that their properties are not arbitrary or subjective. They have determinate features that consciousness discovers rather than creates. This dissolved the epistemological problem that had plagued mathematical Platonism. We do not need causal interaction with mathematical objects to know about them. We need intentional directedness toward them. Consciousness can grasp meanings and essences through acts of ideation, intuiting the universal in the particular, recognizing essential features of concepts. This is how we know mathematical truths. We apprehend the concept of number, and from that apprehension we can see what follows necessarily. Gödel believed phenomenology could also address the problem of evidence in mathematics. What counts as evidence for a mathematical claim? not empirical observation, since mathematics is not about physical reality, not formal proof alone, since proof must start from axioms that themselves need justification. The answer is intuitive evidence, the self-givenness of mathematical structures to consciousness. When we clearly grasp a mathematical concept, certain truths about it become evident. The axioms of set theory, for instance, should be evident when we fully understand what sets are. But how do we distinguish genuine evidence from illusion or error? This is where phenomenological method becomes crucial. By carefully examining our mental acts, by varying examples to identify essential features, by checking for consistency and coherence, we can achieve clarity about concepts. Mathematical intuition is not infallible, but it can be refined and corrected through disciplined phenomenological analysis. Husserl himself had written about the phenomenology of mathematics in his early work, particularly in Philosophy of Arithmetic. He analyzed how we form the concept of number through collecting objects together and abstracting from their particular features. A group of 3 apples, 3 chairs, 3 ideas, all instantiate the same number, 3. We grasp this universal through comparing different instances and recognizing what they have in common. Gödel found this analysis valuable but incomplete. Husserl's early work focused on elementary arithmetic and did not address higher mathematics. Gödel wanted to extend phenomenological method to set theory, transfinite numbers, and the abstract structures mathematicians study. He believed this extension was possible and would vindicate mathematical realism. The relationship between phenomenology and Platonism in Gödel's thought requires careful articulation. Some interpreters argue Gödel abandoned Platonism after discovering phenomenology, replacing talk of abstract objects with talk of ideal meanings given to consciousness. Others argue phenomenology merely provided epistemological support for Platonism without changing the underlying ontology. I think the truth lies between these extremes. Gödel remained committed to mathematical realism, the view that mathematical truths are objective and not reducible to mental constructions. But he reconceived how we access mathematical reality, not through perception of independently existing objects, but through intuition of ideal structures. These structures are objective in that their properties are determined independently of individual minds, but they are not objects in the ordinary sense. They are essences or meanings that consciousness can grasp. This sounds obscure, but consider an analogy. The meaning of a word is not a physical object, yet it is objective. The word triangle means a 3-sided polygon, regardless of what any individual thinks. This meaning is grasped by understanding, not perceived through the senses. Mathematical concepts are similar. They are ideal meanings with objective content, knowable through acts of consciousness directed toward them. This view sits between nominalism and naive Platonism. Nominalism denies that universals exist, treating them as mere names. Naive Platonism posits a realm of abstract objects with the same kind of reality as physical objects. Gödel's phenomenologically informed realism says mathematical concepts exist as ideal meanings, objective but not spatio-temporal, graspable by consciousness, but not arbitrary creations of consciousness. One problem with this position concerns intersubjectivity. If mathematical concepts are meanings given to consciousness, how do different people grasp the same meanings? What guarantees that my concept of set is the same as yours? Without this guarantee, mathematics becomes subjective, with each mind constructing its own meanings. Gödel addressed this through Husserl's notion of intersubjective agreement, grounded in shared essential structures. All human consciousness has the same basic structure, the same forms of intuition, the same logical capacities. When we examine concepts phenomenologically, we discover essences that are the same for everyone. The concept of number is not mine or yours, but an ideal unity accessible to any consciousness capable of grasping it. This raises further questions. Why should human consciousness be structured to grasp mathematical truths? Is there some pre-established harmony between our minds and mathematical reality? Gödel's answer seemed to involve a kind of rationalist optimism. Reason is adapted to reality because both have rational structure. The universe is mathematically intelligible because it embodies mathematical principles, and our minds can grasp these principles because reason participates in the same rational order. This is reminiscent of Leibniz's pre-established harmony, which Gödel admired. It is also reminiscent of Plato's theory that learning is recollection. The soul remembers what it knew before embodiment. Gödel did not explicitly endorse these specific doctrines, but his view implied something similar. Mathematical knowledge is possible because consciousness and mathematical reality share a common rational structure. Critics of phenomenology and of Gödel's appropriation of it have raised several objections. First, phenomenology seems too subjective to ground objective knowledge. If we are just examining our own consciousness, how do we know our findings apply to reality? Second, phenomenological descriptions are often vague and contestable. Different phenomenologists describe the same phenomena differently. Where is the rigor Husserl promised? Third, phenomenology's jargon, terms like intentionality, noesis, noema, eidetic variation, makes it obscure and hard to assess critically. Gödel was aware of these concerns. He criticized Husserl's sometimes sloppy architectonic, preferring more systematic development. He also recognized that phenomenology was only a beginning, not a completed science. But he believed the method was sound and that patient application would yield results. Mathematical phenomenology was a program for the future, not a finished system. One concrete application Gödel envisioned involved analyzing the concept of set phenomenologically. What is given when we grasp the concept of set? We understand that a set is any collection determined by a property or condition. We recognize that sets can be elements of other sets. We see that there is no largest set. The hierarchy extends indefinitely. These insights arise from clarifying the concept through intuition, not from empirical investigation or arbitrary stipulation. From such clarification, we can justify axioms of set theory. The axioms should be evident expressions of what the concept of set involves. When they are not evident, we need further clarification or new intuitions that extend our understanding. This is how mathematical knowledge progresses, through conceptual analysis that reveals structures initially implicit in our intuitive grasp. Gödel never fully developed this program. He wrote fragments and draft papers, but published little on phenomenology. The main source for his views is his conversations with Hao Wang, published decades after Gödel's death. We have enough to see the outlines of his position, but not a fully articulated phenomenological philosophy of mathematics. Still, the turn to phenomenology was philosophically significant for Gödel. It represented an attempt to reconcile realism and rationalism, to explain how reason can know an objective reality without requiring causal interaction with that reality. It provided a method for investigating consciousness and its structures systematically, and it connected Gödel's mathematical work to a broader philosophical tradition concerned with meaning, intentionality, and the foundations of knowledge. Whether phenomenology ultimately succeeds in these tasks is debatable. Many philosophers find it obscure or question whether it delivers on its promises. But Gödel's engagement with it shows his commitment to finding rigorous philosophical methods and his willingness to draw on diverse intellectual traditions. He was not content with narrow technical work in logic. He wanted to understand the nature of mathematical knowledge, the relationship between mind and reality, and the proper method for philosophy. Phenomenology seemed to offer a path toward these goals, even if the path remained incompletely traveled. Part 9. Broader philosophical commitments. When Hao Wang asked Kurt Gödel to characterize his philosophical position, Gödel replied that his theory was rationalistic, idealistic, optimistic, and theological. This compact description captures the 4 pillars supporting his worldview. Understanding what Gödel meant by each term reveals a comprehensive philosophical vision that unified his work in logic, mathematics, physics, and metaphysics. Start with rationalism. Gödel believed that reason is humanity's supreme faculty and that pure reason can reach substantive truths about reality. This distinguishes him from empiricists who think all factual knowledge comes from sensory experience, and from skeptics who doubt reason's power to grasp ultimate truth. For Gödel, mathematical knowledge demonstrates reason's capacity. We know truths about infinity, about abstract structures, about logical necessity, none through empirical observation. This knowledge comes from rational insight, from grasping concepts and recognizing what they entail. But Gödel's rationalism extended beyond mathematics. He thought reason could make progress in metaphysics and theology. The ontological proof exemplifies this, an attempt to establish God's existence through conceptual analysis. His conviction that philosophical problems can be solved, that every meaningful question has an answer, reflects rationalist optimism about reason's power. We may not have the answers yet, but in principle, reason can find them. This rationalism was Leibnizian in character. Leibniz believed the world is fundamentally rational, structured by principles that reason can discover. The principle of sufficient reason, nothing happens without a reason, and the principle of the identity of indiscernibles, things differing in all properties are identical, exemplify such rational principles. Gödel shared this conviction that reality has rational structure. The universe is not chaotic or arbitrary, but ordered according to intelligible laws and principles. One might object that the incompleteness theorems undermine rationalism by showing the limits of reason. If formal systems cannot prove all truths, does this not demonstrate reason's inadequacy? Gödel thought the opposite. Incompleteness shows that reason exceeds any fixed formal system. Our rational capacities are not exhausted by following mechanical rules. We can recognize truths that formal systems miss, and we can invent new axioms extending our systems. This inexhaustible creativity of reason is evidence of its power, not weakness. The second pillar is idealism. We have explored Gödel's idealism about time, his belief that temporal flow and the distinction between past and future are features of consciousness rather than objective reality. But his idealism was more selective and nuanced than traditional German idealism. He was not an idealist about matter or physical objects. Space-time exists objectively. But certain features we naively attribute to reality, intuitive time, perhaps certain modal notions, subjective qualities of experience, are ideal, belonging to the experiencing subject rather than to things in themselves. This selective idealism resembles Kant's transcendental idealism, though Gödel rejected Kant's conclusion that things in themselves are unknowable. Gödel thought we can penetrate beyond appearances to grasp objective truths through reason. Science and mathematics provide such knowledge. What is ideal is not reality itself, but certain structures we impose in experiencing it. There is also an idealist element in Gödel's view of mathematical objects. They are not mind-independent in the way physical objects are. They are ideal structures, essences, or concepts that consciousness can grasp. This does not make them subjective or arbitrary. Mathematical truths are objective, but mathematical reality consists of ideal structures rather than concrete particulars. The third pillar is optimism. Gödel believed that all meaningful problems can be solved, that mathematical and philosophical progress is possible, and that the universe is rationally ordered in a way that minds can comprehend. This optimism was deep-seated and unshaken by his technical results. Yes, formal systems are incomplete. Yes, some questions are undecidable within given frameworks. But we can always extend our frameworks, adopt new axioms, develop better intuitions. There are no absolute barriers to knowledge. This optimism extended to his views about science and human understanding. Gödel thought science would continue progressing toward deeper truths about reality. The incompleteness of current theories does not mean truth is inaccessible, but that inquiry must continue. He was prophetic about developments in set theory, anticipating the importance of large cardinals before their significance became clear. This prophetic insight reflected his optimism that the right ideas would emerge. Some find this optimism naive, especially after the 20th century's horrors: wars, totalitarianism, scientific weapons of mass destruction. How could Gödel remain optimistic? Part of the answer is that his optimism concerned reason and knowledge, not historical progress or human behavior. He did not believe humanity was becoming morally better, or that political problems would solve themselves. His optimism was epistemological. We can know truth. And metaphysical. Reality is intelligible, rather than historical or political. The fourth pillar is theology. Gödel believed in God, an afterlife, and a reality richer than the physical universe. He told friends he was convinced of life after death based on purely rational considerations. He thought the world's rational structure implied a rational creator or ground. His 14-point program included beliefs in other worlds, higher rational beings, and the possibility of exact theology. But Gödel's theology was philosophical rather than sectarian. He was baptized Lutheran, but never joined any religious congregation. He described his belief as theistic, not pantheistic, following Leibniz rather than Spinoza. This means he believed in a personal God, distinct from the universe, not an impersonal divine substance identical with nature. What role did this theology play in his intellectual life? It provided metaphysical grounding for his rationalism and optimism. If the universe has a rational creator, this explains why reality is intelligible and why reason can grasp truth. It also provided motivation for studying philosophy and mathematics. Understanding mathematical structures is understanding the rational order built into creation. Clarifying concepts is discovering the ideas in the divine mind. This sounds mystical, but Gödel did not see it that way. He thought these were rational conclusions following from reflection on the nature of mathematical truth, the intelligibility of the universe, and the power of reason. The ontological proof was an attempt to make this explicit, to show that belief in God follows from properly understanding perfection and necessary existence. Critics can question whether these four pillars cohere. Can you be both a rationalist and an idealist? Rationalism seems to require realism. Reason grasps objective reality. Idealism seems to make reality mind-dependent. But Gödel's selective idealism avoids direct conflict. He was realist about mathematical and physical structures, idealist only about certain experiential features like temporal flow. Can you be both optimistic about reason and acknowledge the incompleteness theorems? Yes, if incompleteness shows reason's creativity rather than its limits. Formal systems are incomplete, but reason can transcend any fixed system. Can you be both rationalistic and theological? Only if theology is rational theology, grounded in philosophical argument rather than revelation or faith. Gödel's theology was philosophical, though it went beyond what most philosophers consider rationally demonstrable. Let me explore several other aspects of Gödel's broader philosophical commitments that emerge from his papers and conversations. One is his belief in conceptual analysis as the proper philosophical method. Philosophy should clarify concepts through systematic examination of their meaning and implications. This is neither empirical investigation nor speculative system building, but patient conceptual work. Phenomenology provided one approach to such analysis, but the goal transcends any particular method. Gödel thought many philosophical disputes arise from confused or unclear concepts. If we could clarify what we mean by causation, time, existence, truth, many traditional problems would dissolve or become tractable. This emphasis on conceptual clarity connected him to analytic philosophy, though he was more ambitious than most analytic philosophers about what conceptual analysis could achieve. Another commitment was to the unity of knowledge. Mathematics, physics, philosophy, theology, these are not separate domains, but aspects of a single, rational investigation of reality. Mathematical structures appear in physics. Physical theories have philosophical implications. Philosophy requires rigorous methods like those in mathematics. This holistic view contrasted with growing specialization and fragmentation in 20th century intellectual life. Gödel also believed in objective truth across domains. Mathematical truth is objective. Physical truth is objective. Even moral and theological truth are objective, though harder to access. This objectivity does not mean we currently possess truth in all areas. It means there is truth to be found, that inquiry aims at discovering how things really are, rather than constructing useful fictions or social conventions. This commitment to objective truth made Gödel an opponent of relativism, conventionalism, and anti-realism in all forms. He rejected logical positivism's verification principle, the claim that meaningful statements must be empirically verifiable. Many important truths, particularly in mathematics and metaphysics, are not empirically verifiable, but are nonetheless meaningful and true. He rejected conventionalism about logic and mathematics, the view that logical and mathematical truths are arbitrary choices rather than discoveries. and he rejected instrumentalism about scientific theories, the view that theories are merely useful tools rather than descriptions of reality. These rejections sometimes put him at odds with prevailing philosophical fashions. The Vienna Circle, which Gödel attended as a young man, promoted logical positivism, but Gödel never accepted their core doctrines. He attended meetings, engaged respectfully, but maintained his realist and rationalist convictions. His incompleteness theorems, ironically, were sometimes taken as supporting positivism by showing the limits of formal systems, but Gödel interpreted them in the opposite direction, as showing that truth transcends formal provability. Another aspect of Gödel's philosophy concerns the relationship between mathematics and reality. He believed mathematical structures are not merely useful for describing physical phenomena, but are somehow constitutive of reality itself. The universe exhibits mathematical order because it is mathematical in some deep sense. This is not just that we can model nature mathematically. It is that mathematical structures are woven into the fabric of reality. This sounds Pythagorean or Platonic, and indeed Gödel felt kinship with these ancient traditions. Modern physics reinforces this view. The equations of quantum mechanics and general relativity are not mere descriptions of how nature behaves, but seem to capture something about what nature fundamentally is. Particles are solutions to wave equations. Space-time is a differentiable manifold with a metric tensor. Mathematical structures are not external to physical reality, but internal to it. If this is right, then studying mathematics is studying the deepest structure of reality. Pure mathematics, pursued for its own sake without regard to applications, reveals truths about the rational order underlying existence. This justified Gödel's life work in logic and set theory. He was not just manipulating symbols or exploring arbitrary formal systems. He was uncovering objective features of the mathematical universe that grounds physical reality. One more philosophical commitment deserves mention: Gödel's belief in progress. Despite recognizing fundamental incompleteness and unsolved problems, he thought mathematical and philosophical knowledge accumulates over time. We understand more now than in past centuries. Future generations will understand more than we do. This progress is not inevitable or automatic, but depends on continued rational inquiry. What enables progress? Partly, the development of better concepts and methods. Partly, the discovery of new axioms and principles that extend our systems. Partly, the refinement of intuition through mathematical practice. And partly, the emergence of rare individuals, like Gödel himself, who make breakthrough discoveries reshaping entire fields. But Gödel also thought philosophical progress was possible, though harder than mathematical progress. Philosophy deals with concepts that are vaguer and more contested than mathematical concepts. Still, by applying rigorous methods, whether phenomenological analysis, logical formalization, or careful argumentation, philosophers can make genuine advances. The history of philosophy is not just a series of disconnected opinions, but a developing investigation where later thinkers build on earlier insights. This belief in progress distinguished Gödel from postmodern skeptics, who see philosophy as endless interpretive play without cumulative knowledge. It also distinguished him from historicists, who think philosophical ideas are so embedded in cultural contexts that later thinkers cannot really improve on earlier ones. Gödel thought truth is timeless, and that reason in any era can approach it more closely. Let me conclude this part by considering whether Gödel's broader philosophical vision hangs together coherently. Can all these commitments, rationalism, selective idealism, optimism, theology, objectivism, progressivism, be maintained consistently? Some tensions are apparent. Rationalism sits awkwardly with idealism if idealism means reality is mind-dependent. Optimism about reason's power seems challenged by incompleteness and undecidability results. Theology based on rational argument strikes many as presumptuous or unjustified. Yet there is also unity. All these commitments flow from a central conviction that reality has rational structure accessible to thought. Mathematical truth is objective because mathematical structures are real. Physical law is intelligible because the universe embodies rational principles. Progress is possible because reason can penetrate deeper into this rational order. God exists because maximal perfection must be real in a rational universe. Time is ideal because it lacks the structure reason finds in relativistic space-time. Whether this vision is ultimately defensible is questionable. Many philosophers and scientists have rejected parts or all of it. Empiricists deny that reason alone can reach substantive truths. Naturalists reject theology and metaphysical speculation. Anti-realists about mathematics deny that mathematical structures exist objectively. Presentists about time reject temporal idealism. But Gödel's vision has power and appeal. It takes seriously both the reality of abstract structures and the capacity of human reason to know them. It refuses to reduce mathematics to formalism or conventionalism. It seeks unity and coherence across domains rather than accepting fragmentation. And it maintains that knowledge and truth matter ultimately, that getting things right is not just pragmatically useful, but intrinsically valuable. This philosophical vision motivated Gödel's technical work and gave it meaning. He was not just proving theorems, but exploring the structure of mathematical reality. He was not just solving logical puzzles, but clarifying the relationship between truth and proof. He was not just discovering new cosmological solutions, but investigating the nature of time. Every technical achievement served a broader philosophical purpose: understanding reality through reason. Part 10. Legacy and Influence. Kurt Gödel died on January 14, 1978, at age 71. In his final years, paranoia about being poisoned had led to self-starvation. His death certificate listed malnutrition and inanition, wasting away. It was a tragic end for one of the 20th century's greatest minds. But the intellectual legacy he left continues to reshape mathematics, logic, computer science, physics, and philosophy decades later. The scope of Gödel's influence is staggering. The Incompleteness Theorems alone would place him among the most important figures in modern thought. They fundamentally changed how mathematicians and philosophers understand the foundations of mathematics. But Gödel also proved the completeness theorem, constructed the constructible universe, discovered rotating cosmological solutions, developed the dialectica interpretation, and contributed to set theory, proof theory, and logic in countless ways. Few thinkers have had such broad and deep impact across multiple fields. Let me trace the legacy through different domains, starting with mathematics itself. The Incompleteness Theorems showed that mathematics cannot be completely formalized. This ended dreams of reducing mathematics to mechanical symbol manipulation. But it also opened new directions. Mathematicians began systematically investigating which statements are independent of which axioms, exploring the hierarchy of logical strength, and studying the relationship between different foundational systems. Set theory, after Gödel, became a rich field exploring the upper reaches of infinity. His work on constructibility and the Continuum hypothesis inaugurated the study of independence phenomena. Paul Cohen's forcing technique, building on Gödel's results, became a central tool. Large cardinal axioms, whose importance Gödel prophetically anticipated, are now fundamental to set theory. The whole enterprise of investigating which statements require which axioms descends from Gödel's recognition that incompleteness and independence are pervasive. Model theory, the study of relationships between formal languages and their interpretations, emerged largely from Gödel's completeness theorem. The techniques he developed for constructing models became standard tools. The Lowenheim-Skolem theorem, compactness, the study of non-standard models, all connect to Gödel's early work. Modern model theory is unthinkable without his foundational contributions. Proof theory also owes much to Gödel. While Hilbert initiated the program, Gödel's incompleteness theorems forced reconception of what proof theory could achieve. The study of consistency strength, ordinal analysis, and the hierarchy of provability followed from recognizing that consistency cannot be proven from within, but only from stronger systems. Gödel's speed-up theorems, showing that some proofs require exponentially longer formulations in weaker systems, opened another research direction. In logic more broadly, Gödel pioneered the use of arithmetic to encode logical syntax. Gödel numbering became a fundamental technique throughout mathematical logic and computability theory. The diagonal argument he used has been adapted to prove many other results. His technical innovations reshaped how logicians approach formalization and metamathematical reasoning. Now turn to computer science, where Gödel's influence is equally profound, though sometimes indirect. The incompleteness theorems connect intimately to computability theory. Alan Turing built on Gödel's work when developing the theory of computation. The halting problem, that no algorithm can determine whether arbitrary programs terminate, is closely related to incompleteness. Both use self-referential constructions to establish negative results about what formal systems can achieve. This connection between logic and computation proved foundational. The Church-Turing thesis, that everything computable is Turing computable, relies on insights from Gödel's work about what can be formalized. Computational complexity theory, which studies how much time and space different problems require, uses techniques descended from Gödel's encoding methods. Automated theorem proving faces limitations implied by Gödel's theorems. No algorithm can find proofs of all true statements. No algorithm can determine whether arbitrary statements are independent of given axioms. These limitations shape what automated reasoning systems can accomplish. Yet within these limits, impressive progress has been made. Modern proof assistants can verify complex mathematical proofs, though they cannot generate them automatically without human guidance. The philosophical debates about artificial intelligence discussed earlier also trace to Gödel's work. Can machines think? Can computation capture all aspects of human intelligence? The Lucas-Penrose arguments invoking Gödel's theorems may fail, but they motivated serious investigation of these questions. contemporary AI research grapples with issues of creativity, insight, and understanding that connect to what the incompleteness theorems reveal about formal systems versus human reasoning. In physics, Gödel's rotating universe solutions remain important, despite not describing our actual universe. They show that general relativity allows exotic causal structures. This stimulated research on causality in curved spacetime, the chronology protection conjecture, and the global properties of spacetime. Physicists now routinely consider whether spacetimes contain closed time-like curves and what physical principles might forbid them. More broadly, Gödel's work on relativity connected to foundational questions about time, determinism, and the structure of spacetime. His argument that relativistic cosmology supports temporal idealism, while controversial, forced philosophers and physicists to think carefully about what general relativity implies for the nature of time. The debate between substantivalists and relationalists about spacetime, between eternalists and presentists about time, all connect to issues Gödel raised. Theoretical physics has also engaged with incompleteness in various ways. Some physicists speculate that certain questions about quantum gravity or string theory might be formally undecidable. Others explore whether the structure of physical law itself might be incomplete in Gödelian fashion. These applications remain tentative and controversial, but they show that Gödel's ideas continue generating new research directions. In philosophy, Gödel's impact is pervasive. Philosophy of mathematics was transformed by his work. The debate between Platonism, formalism, and constructivism became more sophisticated after Gödel showed that truth exceeds provability. His defense of mathematical realism, combined with technical results supporting it, made Platonism respectable among philosophers who might otherwise have dismissed it. Philosophy of logic similarly evolved in response to Gödel. The relationship between syntax and semantics, between proof and truth, between first-order and higher-order logic, all became central topics, partly because of his results. The study of modal logic, particularly the logic of necessity and possibility used in his ontological proof, developed significantly after Gödel's work. Epistemology has engaged with issues raised by incompleteness. How can we have knowledge if our formal systems are incomplete? What role does intuition play in acquiring knowledge? Can reason alone justify beliefs about abstract domains? These questions predate Gödel, but took on new urgency after his theorems. Metaphysics has wrestled with Gödel's views on time, modality, and the nature of abstract objects. The debate about whether time is real or ideal intensified after his rotating universe argument. Discussions of mathematical objects and how we can know about them constantly reference his work. His ontological argument, while not widely accepted, reinvigorated serious discussion of ontological proofs. Philosophy of mind faces questions about whether human thought can be mechanized that connect to incompleteness. While Gödel himself was cautious about drawing strong conclusions, his work provides essential background for debates about computationalism, the nature of understanding, and whether consciousness has non-algorithmic aspects. Now let me address common misconceptions about Gödel's work that have proliferated in popular culture and even in academic discussions. These misunderstandings distort his legacy and obscure what he actually proved. Misconception 1. The incompleteness theorems prove that some things cannot be known. False. The theorems show that some truths cannot be proven within particular formal systems. This is about the limitations of formal proof, not about human knowledge. We can recognize Gödel sentences as true through informal reasoning. What we cannot do is prove every truth using a fixed set of axioms and rules. Misconception 2. Incompleteness means mathematics is uncertain, or that mathematical truth is relative. False. Gödel was a Platonist who believed in objective mathematical truth. His theorems show that truth exceeds formal provability, which actually supports the view that mathematical truth exists independently of our formal systems. Incompleteness does not undermine mathematics, but reveals its inexhaustible depth. Misconception 3. Gödel proved that human minds are not machines. False. Gödel proved no such thing. He was skeptical of mechanism, but did not claim to have a proof. The Lucas-Penrose arguments that tried to derive anti-mechanism from incompleteness have been widely criticized and rejected. The relationship between incompleteness and the nature of mind remains philosophically controversial. Misconception 4. Incompleteness applies to everything, showing that all systems are limited. Overstated. Incompleteness applies to consistent formal systems strong enough to express basic arithmetic. It does not automatically apply to legal reasoning, scientific theories, theological systems, or other domains unless they can be formalized in the relevant way. Extending incompleteness beyond mathematics requires careful argument, not casual application. Misconception 5. Gödel's rotating universe proves time travel is possible, or that time does not exist. Misleading. The rotating universe is an exact solution to Einstein's equations, but does not describe our actual universe. It shows that general relativity allows such spacetimes, which has implications for understanding the theory. But whether time travel is physically possible or whether time is ideal are separate questions, requiring more argument than just pointing to Gödel's solution. Misconception 6. Gödel's ontological proof successfully demonstrates God's existence. Disputed. The proof is logically valid if the axioms are accepted, but the axioms are controversial, and the proof leads to problematic consequences like modal collapse. Most philosophers reject it, though some defend modified versions. At best, it shows what follows from certain assumptions about perfection and necessity. These misconceptions matter because they lead to misapplication of Gödel's results. When journalists, popularizers, or even academics carelessly invoke Gödel to support sweeping claims about limits of knowledge, relativity of truth, or impossibility of AI, they distort his legacy. Gödel's actual achievements are profound enough without inflating them with false implications. Let me also address Gödel's personal influence on individuals and institutions. At the Institute for Advanced Study, he was a legendary figure. His daily walks with Einstein became iconic. Younger mathematicians and logicians sought his advice. His technical brilliance combined with philosophical depth made him a unique intellectual presence. Students and colleagues remember Gödel as extremely rigorous and careful, sometimes to excess. He would question assumptions others took for granted. He demanded precise formulations. This made him an exacting but valuable interlocutor. Many important results in logic and foundations emerged from researchers trying to answer questions Gödel posed or clarify points he raised. Gödel published relatively little after the 1940s, preferring to work on problems until satisfied his results were definitive. This perfectionism meant some important work remained unpublished, only emerging from his notebooks after death. But it also meant that what he did publish was typically of the highest quality and lasting significance. His personal eccentricities, paranoia, hypochondria, reclusiveness in later years, sometimes overshadow his intellectual achievements in biographical accounts. But those who knew him emphasized his brilliance, his philosophical seriousness, and his personal kindness. He mentored students, corresponded extensively with other thinkers, and engaged generously with ideas even when disagreeing. Now consider contemporary relevance. Why should anyone today care about Gödel's work? Several reasons stand out. First, foundational questions he addressed remain unresolved. The continuum hypothesis is still independent of standard axioms. The search for new axioms that Gödel advocated continues. The philosophical interpretation of incompleteness is debated. His work is not historical artifact, but living contribution to ongoing inquiry. Second, as computation becomes increasingly central to science and society, the limits Gödel revealed matter practically. Understanding what can and cannot be computed, what can and cannot be formally verified, what can and cannot be decided algorithmically, all connect to incompleteness and computability theory, descending from Gödel's work. Third, artificial intelligence raises questions about machine intelligence, human understanding, and the nature of thought that relate to Gödel's theorems. As AI systems become more sophisticated, understanding their limitations becomes crucial. Gödel's work provides perspective on what formal systems can achieve and where human insight remains necessary. Fourth, foundational crisis has not disappeared from mathematics and physics. String theory faces questions about empirical testability and uniqueness. Quantum mechanics faces interpretive puzzles. Set theory faces questions about which axioms to accept. Gödel's example of using rigorous mathematical methods to address foundational issues remains relevant for contemporary foundational debates. Fifth, his philosophical vision of unified rational inquiry addressing fundamental questions appeals to those dissatisfied with narrow specialization. Gödel showed how technical work and philosophical reflection can enrich each other. His example suggests that deep understanding requires both formal mastery and conceptual breadth. Let me also note areas where Gödel's influence could be stronger but is not. His philosophical work on phenomenology, though important to him, has had limited impact. Most mathematicians and logicians are unaware of his engagement with Husserl. His views on time, while discussed by philosophers of physics, have not reshaped that field as much as his logical work reshaped logic. His theological interests remain marginal to most academic engagement with his work. The ontological proof is studied as a logical curiosity more than a serious argument for God's existence. His rationalistic optimism and belief in exact philosophy face skepticism from postmodern and naturalistic currents in contemporary philosophy. Still, there are signs of renewed interest in Gödel's broader philosophical vision. Recent scholarship explores connections between his technical and philosophical work more carefully. The publication of his collected works and correspondence has made his unpublished writings accessible. Philosophical commentaries and biographies have appeared, giving fuller pictures of his thought. Let me conclude by considering what Gödel's life and work exemplify. He showed that rigorous formal methods can illuminate the deepest questions about knowledge, truth, and reality. He proved that technical brilliance and philosophical depth need not be separate. He demonstrated that foundational questions matter not just abstractly, but for understanding the structure of thought and the limits of knowledge. Gödel also embodied intellectual courage. He developed positions like mathematical Platonism In an era of formalism, temporal idealism in tension with common sense, rational theology when metaphysics was out of fashion, that were unfashionable or controversial. He pursued them because he thought they were true, not because they were popular. His combination of logical rigor and speculative boldness distinguished him. He would not assert anything without careful argument, yet he was willing to consider ideas others dismissed. He took seriously ancient philosophical questions while using modern mathematical tools to address them. This synthesis of classical philosophical concerns with contemporary formal techniques defines his approach. The incompleteness theorems remain his most famous achievement, but his legacy encompasses far more. He showed that mathematics has inexhaustible depth, that formal systems have inherent limitations, that truth transcends provability. He constructed path-breaking models in set theory and cosmology. He defended mathematical Platonism philosophically and technically. He explored connections between logic, mathematics, physics, and metaphysics. Most fundamentally, Gödel demonstrated that reason can penetrate reality's deepest structures, even while recognizing its own limits. The incompleteness theorems do not counsel despair, but reveal opportunity. There will always be new truths to discover, new axioms to recognize, new concepts to clarify. Mathematics and philosophy remain open-ended investigations, where creativity and insight are eternally necessary. In this sense, Gödel's work is profoundly humanistic. It shows that human thought cannot be mechanized or exhausted by formal systems. It affirms that understanding requires more than following rules. It requires intuition, judgment, and creativity that transcend algorithm. While machines can prove theorems and manipulate symbols, genuine mathematical understanding involves grasping concepts and recognizing truths that no fixed procedure generates. This message remains vital in an age increasingly dominated by computation and formal methods. Gödel reminds us that rigor and formalization are valuable tools, but cannot replace thought. They make explicit what we understand, but cannot generate understanding mechanically. Mathematics and philosophy require human insight that no computer, however powerful, can replicate without fundamentally new principles. Kurt Gödel's intellectual journey, from the incompleteness theorems through Platonism, set theory, cosmology, phenomenology, and theology, represents one of the most remarkable achievements in the history of thought. His work reshaped multiple fields and continues generating insights decades after his death. Understanding what he proved, what he believed, and why he pursued the questions he did enriches our grasp of mathematics, logic, philosophy, and the nature of rational inquiry itself. His legacy is not settled. Debates continue about the interpretation of incompleteness, the viability of Platonism, the nature of time, the prospects for artificial intelligence, the status of mathematical truth. These debates show that Gödel raised questions too deep for easy answers. He challenged us to think carefully about foundations, to maintain intellectual rigor while pursuing ambitious ideas, and to believe that reason can uncover truth even in the face of inherent incompleteness. That is the final lesson. Incompleteness is not defeat, but recognition that the mathematical universe is richer than any finite axiomatization. The journey toward understanding has no end, but every step reveals new vistas. Gödel maps some of that territory with unprecedented precision, showing both how far reason can reach and how much remains to discover. His life work exemplifies the pursuit of truth through reason, rigorous, profound, and ultimately inexhaustible.